In the constellation Cetus, about 787 million light-years from Earth, lies Holmburg 15A, a galaxy so massive it strains comprehension. This supergiant elliptical contains an estimated 2 to 3 trillion stars, making it dozens of times more massive than the Milky Way. Yet its true significance lies at its core. Holmburg 15. A hosts an ultramassive black hole weighing roughly 22 to 40 billion suns, one of the largest ever identified in the nearby universe. Such an object pushes the limits of current theories about black hole growth. This galaxy was not built quietly. Over billions of years, Holmburg 15A grew through repeated, violent mergers with other galaxies, each collision adding stars and funneling material into its central black hole. The scars of this history remain visible in its unusually faint core and the abnormal motions of its stars. Understanding Holmburg 15A means understanding some of the most fundamental processes that shape our universe: how galaxies grow, how supermassive black holes form, and what happens when objects of unimaginable mass collide in the darkness of space. A supergiant in the heart of Abell 85. Holmburg 15. A does not exist in isolation. It occupies a privileged and powerful position as the brightest cluster galaxy, commonly abbreviated as BCG, at the very center of the Abell 85 galaxy cluster. Abell 85 is not just a loose association of galaxies drifting through space. It is a massive, gravitationally bound system containing more than 500 known galaxies, along with vast amounts of dark matter and hot X-ray emitting gas. Galaxy clusters like Abell 85 represent the largest stable structures in the universe, the final stage of cosmic assembly where matter has collapsed into immense, long-lived configurations. Over billions of years, gravity has drawn galaxies together into these clusters, transforming once isolated systems into members of dense cosmic environments. Within Abell 85, galaxies move through a deep gravitational potential well, interacting, colliding, and merging over cosmic time. The cluster spans several million light-years across, making it a true cosmic metropolis. At its heart sits Holmburg 15A, the dominant resident. It is not merely one galaxy among many, but the gravitational anchor of the cluster itself. Its central location is both a cause and a consequence of its extreme mass. As galaxies fall toward the cluster's center, Holmburg 15A grows ever larger by absorbing them, gradually establishing itself as the cluster's undisputed heavyweight. Abell 85 was first catalogued in the 1950s as part of George Abell's groundbreaking survey of rich galaxy clusters. Abell's work provided astronomers with the first systematic map of these enormous structures, revealing that galaxies were not evenly distributed across the universe, but arranged in vast clusters and superclusters. At the time, Abell 85 appeared to be a fairly typical rich cluster. Its true nature, and especially the extraordinary properties of its central galaxy, would only become clear decades later as astronomical instruments improved and observational techniques became more sophisticated. The galaxy we now call Holmburg 15A was discovered earlier, around 1937, by the Swedish astronomer Erik Holmberg. This was a formative era in astronomy, when the very nature of galaxies was still being actively debated. Only a decade earlier, astronomers had finally accepted that spiral nebulae were not nearby clouds of gas, but entire galaxies, island universes located far beyond the Milky Way. Holmburg was among the scientists exploring how these galaxies were distributed through space, searching for patterns and clustering that might reveal the large-scale structure of the universe. Holmburg identified this galaxy as part of his broader work on galactic distributions, noting it as a particularly bright and massive object within a cluster environment. At the time, however, it was impossible to measure its true scale or internal properties. To Holmburg and his contemporaries, it was simply another luminous elliptical galaxy, one entry among thousands in an expanding catalogue. The idea that it might host one of the most extreme black holes ever discovered was far beyond what the observational tools of the era could support. For much of the 20th century, Holmberg 15A remained largely unremarkable. A known object, but not yet a famous one. That perception began to change with the rise of modern astronomy. Advances in spectroscopy allowed astronomers to measure the motions of stars within distant galaxies, while space-based telescopes removed the blurring effects of Earth's atmosphere. These tools revealed that Holmberg 15A was not merely large, but exceptional even by the standards of brightest cluster galaxies. Its sheer size, mass, and unusual internal structure set it apart from nearly every other galaxy studied. To understand why Holmberg 15A is so extreme, it helps to understand what astronomers mean by a supergiant elliptical galaxy. Elliptical galaxies come in a wide range of sizes, from small dwarf ellipticals containing just a few million stars to enormous giants that rival entire clusters in mass. Supergiant ellipticals represent the uppermost end of this spectrum. They are the most massive and luminous galaxies known, almost always found at the centers of galaxy clusters, where gravitational forces are strongest. Unlike spiral galaxies such as the Milky Way, elliptical galaxies lack well-defined structures like arms, disks, or dust lanes. They contain very little cold gas and dust, the raw materials needed to form new stars. As a result, star formation in ellipticals largely ceased billions of years ago. What remains is an ancient stellar population composed mostly of old red stars orbiting in random directions. This random motion gives ellipticals their smooth, featureless appearance when viewed from afar. Holmberg 15A exemplifies all of these traits, but on a staggering scale. Its stellar mass is estimated to be on the order of 2 trillion times the mass of the Sun. That translates to roughly 2 to 3 trillion stars, an order of magnitude more than the Milky Way, which contains around 200 billion. If placed side by side, Holmberg 15A would utterly dwarf our galaxy. There are no spiral arms, no bright star-forming regions, and no obvious internal structure. Instead, it presents itself as a vast, glowing ellipsoid of ancient starlight, its brightness gradually fading toward its edges. The reason Holmberg 15A has grown so enormous lies in its position at the center of Abell 85. In galaxy clusters, the central galaxy occupies the lowest point in the cluster's gravitational potential well. Over time, this location acts like a cosmic trap. Smaller galaxies that pass too close lose energy through gravitational interactions and spiral inward. As they approach the center, tidal forces stretch and tear them apart, stripping away their stars. Those stars do not vanish. They are absorbed into the halo of the central galaxy. This process, known as galactic cannibalism, has been operating in Abell 85 for billions of years. Computer simulations show that brightest cluster galaxies can grow several times their original mass through repeated mergers and accretion events. Holmberg 15A is the end product of this long and violent history. Each galaxy it consumes adds to its size, its mass, and its dominance. Rather than forming new stars, it grows by collecting old ones, assembling itself piece by piece from the remnants of its neighbors. Over time, this process concentrates a significant fraction of the cluster's total stellar mass into a single, colossal galaxy. Observing Holmberg 15A is no small feat due to its immense distance from Earth. The galaxy lies approximately 787 million light-years away, meaning the light we detect today left the galaxy nearly 800 million years ago. We are seeing Holmberg 15A as it existed long before complex life appeared on Earth. During its journey through space, that light has been stretched by the expansion of the universe, shifting it toward longer, redder wavelengths, a phenomenon known as cosmological redshift. By measuring this redshift, astronomers can determine the galaxy's distance and place it accurately within cosmic history. Despite this vast distance, modern observatories have been able to study Holmberg 15A in remarkable detail. Space-based telescopes, like the Hubble Space Telescope, provide sharp images of its smooth stellar distribution, while large ground-based telescopes, equipped with adaptive optics, correct for atmospheric distortion. Spectroscopic instruments measure how stars move within the galaxy, revealing the gravitational forces at work in its core. It was these measurements, subtle deviations in stellar motion near the center, that first hinted something extraordinary was hiding there. At the heart of Holmburg, 15A, lies a central region unlike that of typical elliptical galaxies. Instead of a dense concentration of stars, astronomers observed an unusually large, diffuse core where stars appeared to be missing. This strange feature could not be explained by ordinary galactic evolution. It pointed toward an unseen influence of immense gravitational power, evidence that would ultimately lead astronomers to propose the presence of an ultramassive black hole. That discovery would elevate Holmburg 15A from an unusually large galaxy to one of the most extreme objects ever studied, offering a rare glimpse into the upper limits of cosmic structure and black hole growth. The mysteriously dim core. One of the most striking features of Holmburg 15A is its core, or rather the lack thereof. When astronomers first obtained high-resolution images of the galaxy, they noticed something peculiar. The very center of the galaxy, where they expected to see the brightest concentration of stars, was oddly faint. This was not what they anticipated. In most elliptical galaxies, the stellar density increases steadily toward the center, creating a bright nucleus where millions of stars orbit in a relatively small volume. But Holmburg 15A showed the opposite behavior. Its center was depleted, containing far fewer stars than expected. The core radius, the size of this dim central region, measures approximately 15,000 light-years across, making it one of the largest known depleted cores in any galaxy. To an astronomer, this was immediately suspicious. Something had excavated the galaxy's core, removing or ejecting a tremendous amount of stellar mass from the central region. Depleted cores are not unique to Holmburg 15A. They appear in many massive elliptical galaxies, particularly those found at the centers of galaxy clusters. But the core in Holmburg 15A is exceptionally large and exceptionally faint. Photometric measurements showed that the galaxy's central region is about 2 magnitudes fainter than the faintest depleted cores previously observed in other galaxies. In astronomical terms, a magnitude difference of 2 means the center of Holmburg 15A is about 6.3 times dimmer than it should be based on comparisons with similar galaxies. This extreme depletion suggested that an extraordinary amount of mass had been removed from the core. Somewhere between 1 and 2 trillion solar masses of stars were simply missing from where they should have been. The question was, what could create such a massive stellar deficit? The leading explanation involves supermassive black holes, specifically what happens when 2 of them merge. When 2 large galaxies collide and merge, their central black holes eventually sink to the center of the newly formed galaxy. For a time, they orbit each other, forming a binary black hole system. As they orbit, these black holes interact gravitationally with nearby stars through a process called dynamical friction. Stars that pass close to the black hole pair can be flung outward at high velocities through gravitational slingshots, similar to how spacecraft gain speed when they fly past planets. This process, known as core scouring, progressively removes stars from the galactic center. The black holes act like cosmic billiard balls, knocking stars out of the core region with each orbit. Over hundreds of millions, or even billions of years, this process can excavate a significant stellar deficit, leaving behind a depleted core with far fewer stars than originally present. Computer simulations of galaxy mergers have successfully reproduced the observed properties of depleted cores. These simulations start with 2 elliptical galaxies, each containing a supermassive black hole. As the galaxies merge, their black holes spiral inward toward the center of the remnant galaxy. Initially, they lose energy through dynamical friction. Their gravitational interactions with stars in the galaxy cause them to slow down and sink toward the center. Once they get close enough, the black holes form a tight binary. At this stage, stars that venture near the binary can be ejected at high speeds, carrying away orbital energy from the black hole pair. This causes the binary to shrink further, eventually reaching the point where gravitational waves become important. The emission of gravitational waves carries away the final bit of orbital energy, causing the black holes to merge into a single, more massive black hole. The entire process leaves behind a galaxy with a depleted core, and the size of that core correlates directly with the mass of the resulting black hole. The correlation between core size and black hole mass is one of the most important relationships in extragalactic astronomy. Dozens of galaxies with depleted cores have been studied, and in nearly every case where the black hole mass can be measured directly, there is a tight relationship. Larger cores harbour more massive black holes. The relationship is almost linear on a logarithmic scale, meaning that a core twice as large typically contains a black hole roughly twice as massive. For Holmburg 15A, the exceptionally large core radius of 15,000 light-years immediately suggested that the galaxy must contain an exceptionally massive black hole. Early estimates based solely on the core size predicted a black hole mass somewhere in the range of tens of billions of solar masses. This made Holmburg 15A an obvious target for follow-up observations aimed at directly measuring the black hole's mass by studying the motions of stars near the galactic center. However, obtaining those measurements proved exceptionally challenging. The very feature that made Holmburg 15A interesting, its ultra-faint core, also made it extremely difficult to observe. To measure a black hole's mass directly, astronomers need to obtain high-quality spectra of stars orbiting near the black hole. These spectra reveal the star's velocities through the Doppler effect. Stars moving toward us show light shifted toward bluer wavelengths, while stars moving away show light shifted toward redder wavelengths. By mapping out the velocity field in 3 dimensions, astronomers can determine how fast stars are orbiting and thus calculate the mass of the object they are orbiting around. But this technique requires detecting individual stars, or at least resolving small groups of stars. And the depleted core of Holmburg 15A is so faint that even with the best telescopes, the signal from the central stars is extremely weak. Many galaxies at similar distances have bright cores that make spectroscopy relatively straightforward. Holmburg 15A, perversely, presents the opposite problem: Erich Holmberg's discovery and early observations. Erich Holmberg's career coincided with a revolutionary period in astronomy when the nature of galaxies was being fundamentally rewritten. Born in Sweden in 1908, Holmburg became one of the leading astronomers of his generation, known for his meticulous observational work and innovative approaches to studying galaxy clusters. In the 1930s and 1940s, the astronomical community was still grappling with the realization that the universe extended far beyond the Milky Way. Edwin Hubble had only recently proven that spiral nebulae were actually distant galaxies in their own right, fundamentally expanding humanity's conception of cosmic scale. Within this context, Holmberg set out to systematically study how galaxies were distributed in space and whether they showed any tendency to cluster together. His work required painstaking examination of photographic plates taken with large telescopes, identifying faint smudges of light and measuring their positions on the sky. The galaxy that would later bear his name appeared in these surveys as an unremarkable elliptical galaxy in the constellation Cetus. At the time, Holmberg could measure its apparent brightness and estimate its size, but the technology to determine its distance accurately did not yet exist. Spectroscopy, the technique of splitting light into its component colors to reveal information about an object's motion and composition, was still in its infancy for faint galaxies. Holmberg noted the galaxy's position and classified it based on its appearance, but there was little he could determine about its physical properties. It was simply one more galaxy added to the growing catalogues that astronomers were compiling as they mapped the universe's large-scale structure. The galaxy's designation, Holmburg 15A, indicates it was the brightest member A of the 15th group in his catalogue. The fact that it was the dominant galaxy in its group suggested it was substantial, but nothing about Holmberg's initial observations hinted at the monster lurking at its core. The Abell 85 cluster itself was not formally catalogued until the 1950s, when George Abell published his comprehensive survey of rich galaxy clusters. Abell's catalogue was based on systematic examination of photographic plates from the Palomar Observatory Sky Survey, and it identified over 4,000 galaxy clusters based on their richness, the number of galaxies they contained, and their compactness. Abell 85 qualified as a rich cluster with hundreds of member galaxies, and the galaxy at its center, already known from Holmberg's earlier work, was clearly the dominant member. In the decades that followed, Abell 85 became a target for studies of galaxy clusters, particularly after X-ray observatories revealed that galaxy clusters contain vast quantities of hot gas trapped in the cluster's gravitational well. This hot gas emits X-rays and provides a powerful tool for probing the cluster's mass distribution and dynamics. Early observations of Abell 85 revealed that the cluster had a complex structure. X-ray images from satellites like Einstein and Rosart showed that the distribution of hot gas was not smooth and symmetric, as would be expected for a relaxed, stable cluster. Instead, the gas showed evidence of disturbances, regions where it was compressed or heated, suggesting that the cluster was still dynamically active. Observations revealed the presence of subclusters, smaller groups of galaxies that were in the process of falling into the main cluster and merging with it. One particularly prominent subcluster, located to the south of the main cluster center, showed a long tail of X-ray emitting gas stretching behind it. This tail was the result of ram pressure stripping. As the subcluster plowed through the hot gas filling the main cluster, the gas in the subcluster was stripped away like water droplets blown off a car in a windstorm. The existence of these features indicated that Abell 85 was not a quiet, relaxed system, but rather a cluster that had experienced significant merger activity relatively recently in cosmic terms. By the 1990s, when the Hubble Space Telescope became operational, astronomers finally had the resolution needed to study the detailed structure of Holmburg 15A. Hubble's cameras could resolve features in distant galaxies that were simply impossible to see from ground-based telescopes due to the blurring effects of Earth's atmosphere. Images of Holmburg 15A revealed its smooth elliptical structure, but also showed the first hints of the depleted core. When astronomers carefully measured the distribution of light in the galaxy, plotting how the surface brightness changed with distance from the center, they found that the center was surprisingly faint. Instead of the light profile continuing to rise all the way to the nucleus, as seen in most elliptical galaxies, the profile flattened out in the central region. This flattening, or core, extended outward for several thousand light years before the light profile resumed its normal behavior. It was the first direct evidence that something unusual was happening in the center of Holmburg 15A. The discovery of the depleted core raised immediate questions about the galaxy's formation history. Depleted cores are understood to result from galaxy mergers involving supermassive black holes, but creating a core as large as the one in Holmburg 15A would require either an exceptionally massive black hole or multiple mergers. Some astronomers proposed that the galaxy might have undergone not just one, but several major mergers, with each event contributing to the excavation of the core. Others suggested that the galaxy might have experienced a particularly energetic merger that ejected an unusually large number of stars. A third possibility was that the central black hole was simply more massive than expected, capable of clearing out a larger region through core scouring. Distinguishing between these scenarios would require detailed dynamical modeling based on observations of stellar motions, but obtaining such observations for a galaxy as distant and as faint in its core as Holmburg 15A was a formidable technical challenge. The 2019 breakthrough, MUSE at the Very Large Telescope. The breakthrough came in 2019 when an international team of astronomers led by Kianush Mergan at the Max Planck Institute for Extraterrestrial Physics published the first direct dynamical measurement of the black hole mass in Holmburg 15A. Their key advantage was access to one of the most powerful spectrographs in the world, the Multi-Unit Spectroscopic Explorer, or MUSE, mounted on the Very Large Telescope in Chile. MUSE represented a revolution in astronomical spectroscopy. Unlike traditional spectrographs that observe one object at a time or use fibers to sample discrete points in the sky, MUSE is an integral field spectrograph capable of simultaneously obtaining spectra for every point in a two-dimensional field of view. It essentially creates a three-dimensional data cube, two spatial dimensions, plus one wavelength dimension. This allows astronomers to map the spectrum across an extended object like a galaxy, obtaining tens of thousands of individual spectra in a single observation. The technical capabilities of MUSE made it ideal for studying Holmberg 15A. The instrument could observe a field approximately 1 by 1 arc-minute on the sky with high spatial resolution, covering the central region of the galaxy where the black hole's gravitational influence would be strongest. Even though the core of Holmberg 15A is faint, MUSE's sensitivity and efficiency allowed the team to detect spectral features from the integrated light of stars in the core region. The observations were conducted over multiple nights to accumulate sufficient signal-to-noise, resulting in high-quality spectra covering a contiguous area spanning about 100 arc-seconds across. This spatial coverage was critical because measuring a black hole's mass requires mapping the stellar velocity field across a large enough region to capture both the region dominated by the black hole's gravity and the outer regions where the galaxy's overall mass dominates. The team extracted stellar kinematics, the velocities of stars measured from their spectral lines, across the entire field. The Doppler shift of spectral lines reveals whether stars are moving toward or away from us, while the broadening of those lines indicates the random motions of stars in the line of sight. By combining these measurements, astronomers can reconstruct the full three-dimensional velocity field. What they found in Holmberg 15A was particularly interesting. The velocity field showed a low amplitude rotation, with stars on one side of the galaxy moving toward us and stars on the other side moving away. But the rotation speed was only about 20 kilometers per second, much slower than typical for elliptical galaxies. Additionally, the kinematic axis, the line around which the galaxy appeared to rotate, was significantly misaligned from the galaxy's photometric major axis, the line along which the galaxy appears most elongated. This misalignment is a strong indicator that the galaxy is not axisymmetric, but rather triaxial, shaped somewhat like a football with 3 unequal axes. To convert these kinematic measurements into a black hole mass, the team employed a sophisticated technique called Schwarzschild orbit modeling. This method treats the galaxy as a collection of stars moving on various orbits in the combined gravitational potential of the black hole, the stars, and any dark matter halo. The computer generates thousands of possible stellar orbits and then determines which combination of orbits, weighted appropriately, can reproduce the observed light distribution and velocity field. By systematically varying the black hole mass and other parameters, the model searches for the best fit to the data. If the black hole mass is too small, the model cannot reproduce the observed velocities in the central region where the black hole's gravity dominates. If the black hole mass is too large, the predicted velocities would be higher than observed. The best fit model represents the most likely black hole mass given the available data. The results were staggering. The Schwarzschild modeling indicated a black hole mass of 40 billion solar masses, with an uncertainty range of plus or minus 8 billion solar masses. This made the black hole in Holmberg 15A not just massive, but ultramassive, a term reserved for black holes exceeding 10 billion solar masses. To put this in perspective, the supermassive black hole at the center of our Milky Way, known as Sagittarius A star, has a mass of about 4 million solar masses. The black hole in Holmberg 15A is 10,000 times more massive. Even compared to other known ultramassive black holes, Holmberg 15A stood out. The previous record holders, such as the black holes in NGC 4889 and NGC 1600, had masses of about 21 billion and 17 billion solar masses, respectively. Holmberg 15A's black hole was roughly twice as massive as these already extreme objects. The discovery immediately raised important questions. How did such an enormous black hole form? The standard picture of supermassive black hole growth involves two main mechanisms: accretion of gas from the surrounding galaxy and mergers with other black holes during galaxy collisions. For the Holmberg 15A black hole to reach 40 billion solar masses, either it must have accreted an enormous amount of gas over billions of years, or it grew primarily through mergers with other massive black holes. Given that Holmberg 15A sits at the center of a rich galaxy cluster and shows clear evidence of multiple past mergers, The latter explanation seemed more plausible. The galaxy's depleted core supported this interpretation. Core scouring is a direct consequence of black hole mergers. The size of the core correlated well with the measured black hole mass, fitting the established trend that larger cores harbour more massive black holes. However, even accounting for multiple mergers, a 40 billion solar mass black hole pushes the boundaries of theoretical expectations. There are physical limits to how large black holes can grow. If a black hole is actively accreting matter, the infalling material forms an accretion disk that heats up and radiates enormous amounts of energy. This radiation exerts an outward pressure on surrounding gas, counteracting the black hole's gravitational pull. When the luminosity reaches a critical value called the Eddington limit, the outward radiation pressure balances the inward gravitational force, effectively shutting off further accretion. For a 40 billion solar mass black hole, the Eddington luminosity is staggeringly high, but it also means the black hole cannot grow arbitrarily large through steady accretion. The most likely path to such extreme masses involves hierarchical mergers. Smaller black holes merge to form larger ones, which merge again to form even larger ones, and so on. Each merger also produces gravitational waves, ripples in space-time that carry away energy and angular momentum. The revised estimate, 22 billion solar masses. The story of Holmburg 15A's black hole took another turn in early 2025, when a new study, published in January, presented a revised estimate of the black hole mass. Led by Emily Leopold and using observations from the Keck Observatory in Hawaii, this study employed an even more sensitive instrument called KCWI, the Keck Cosmic Web Imager, to obtain a new set of stellar kinematics for the galaxy. Like MUSE, KCWI is an integral field spectrograph, but it offered superior sensitivity for observing the faint central region of Holmburg 15A. The new observations covered a similar spatial extent to the previous MUSE data, but achieved better signal-to-noise, allowing for more precise measurements of stellar velocities. Additionally, the team took advantage of improved orbit modelling techniques, specifically using a triaxial version of the Schwarzschild code called TriOS, which explicitly accounts for the galaxy's non-axisymmetric shape. The critical improvement in this study was recognizing that Holmburg 15A is strongly triaxial. Most previous black hole mass measurements assume galaxies are axisymmetric, meaning they have rotational symmetry around one axis. But the kinematic misalignment observed in Holmburg 15A, the fact that the rotation axis does not align with the photometric major axis, indicated that this assumption was invalid. A triaxial galaxy has three different principal axes, like an ellipsoid with three unequal dimensions. Stars in such a galaxy move on more complex orbits, and assuming axisymmetry when fitting the data can lead to systematic errors in the derived black hole mass. By using a fully triaxial model, the new study aimed to remove this potential bias. The team created approximately 40,000 different galaxy models, each with different combinations of black hole mass, stellar mass distribution, and orbital structure, and searched for the combination that best matched the observations. The result of this extensive modelling was a revised black hole mass of 22 billion solar masses. This is still enormous, still one of the most massive black holes known, but it represents nearly a factor of 2 reduction compared to the earlier estimate. The quoted uncertainty was relatively small, reflecting the high quality of the new data and the robustness of the triaxial modelling. The discrepancy between the 2019 and 2025 measurements highlights an important aspect of black hole mass estimation. These measurements are model-dependent. Different assumptions about the galaxy's structure, the distribution of dark matter, and the orbital structure of stars can lead to different derived masses. The earlier measurement, while groundbreaking, relied on the assumption of axisymmetry. When the newer study accounted for the galaxy's triaxial shape, the best fit black hole mass decreased. This does not mean the original measurement was wrong per se, but rather that it was based on a simpler model that did not capture all the complexity of the galaxy's structure. The revised mass of 22 billion solar masses still places the Holmburg 15A black hole among the most massive in the local universe. It remains larger than the black holes in NGC 4889 and NGC 1600, and significantly larger than the 10 billion solar mass black holes found in galaxies like NGC 1600. The key point is that even with the downward revision, Holmburg 15A hosts an ultramassive black hole at the extreme end of the mass distribution. This is important because the existence of such massive black holes provides critical tests of our theories of black hole and galaxy co-evolution. If black holes could routinely grow to masses of 100 billion solar masses or more, it would require a revision of our understanding of the physical processes that limit black hole growth. The fact that Holmburg 15A, despite being one of the most massive galaxies in the local universe, has a black hole mass only around 20 to 40 billion solar masses suggests that there are indeed limits to how large these objects can grow. The revised measurement also improves our understanding of the relationship between black hole mass and other galaxy properties. One of the most fundamental scaling relations in extragalactic astronomy is the M-sigma relation, which correlates black hole mass with the velocity dispersion of stars in the galaxy's bulge. Velocity dispersion is a measure of the random motions of stars. Higher dispersion means stars are moving faster on average. The M-sigma relation is remarkably tight, spanning multiple orders of magnitude in black hole mass, and it suggests a deep connection between the growth of black holes and the formation of galactic bulges. However, at the very high mass end, the relation appears to bend or break. The most massive galaxies and the most massive black holes do not quite follow the same trend as lower mass system. The new measurement for Holmburg 15A helps to better define this high mass regime, showing that even the most extreme black holes follow predictable scaling relations, albeit with some scatter. Another important implication of the revised mass concerns the size of the black hole's event horizon and whether it might be directly imageable with radio telescope. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole, capturing the shadow of the supermassive black hole at the center of the galaxy M87. This was possible because M87's black hole is both very massive, about 6.5 billion solar masses, and relatively nearby, making its event horizon subtend a large angular size on the sky. The Holmburg 15A black hole, with a mass of 22 to 40 billion solar masses, is more massive than M87's, but it is also much farther away. The angular size of its event horizon, as seen from Earth, is estimated to be around 18 microarc seconds, roughly 1,000 times smaller than a milliarc second. The current resolution of the Event Horizon Telescope is about 20 microarc seconds, which means Holmburg 15A's black hole is tantalizingly close to being resolvable, but probably just below the current detection threshold. Future improvements to the Event Horizon Telescope, such as adding more telescopes to the array or observing at higher frequencies, might eventually allow direct imaging of this black hole's shadow. The physics of ultramassive black holes. Ultramassive black holes, like the one in Holmburg 15A, occupy a special place in astrophysics because they push the boundaries of what black hole physics allows. At the most fundamental level, a black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. The boundary of this region is the event horizon, and for a non-rotating black hole, the radius of the event horizon, the Schwarzschild radius, is directly proportional to the black hole's mass. For a 22 billion solar mass black hole, the Schwarzschild radius is approximately 65 billion kilometers, or about 440 times the distance from Earth to the Sun. This is roughly the size of our entire solar system out to the orbit of Pluto. Within this enormous sphere, space-time is so severely warped that all paths lead inexorably inward toward the singularity at the center. Anything crossing the event horizon is lost forever, adding its mass and energy to the black hole. The formation of ultramassive black holes remains one of the great puzzles in astrophysics. We know that supermassive black holes with millions or even billions of solar masses exist at the centers of most large galaxies, but how they reached such enormous masses is still debated. There are several theoretical pathways. One possibility is that they grew from smaller seed black holes formed in the early universe. These seeds might have been the remnants of the first generation of massive stars, which collapse to form black holes with masses of tens or hundreds of solar masses. Over billions of years, these seed black holes could grow by accreting gas from their surroundings and by merging with other black holes when their host galaxies collided. Computer simulations show that hierarchical merging, where small black holes merge to form larger ones in a cosmic pyramid scheme, can produce supermassive black holes by the present day. However, reaching masses of 20 to 40 billion solar masses through this process requires either very efficient accretion or many mergers. Accretion is limited by the Eddington limit. A black hole accreting at the maximum rate can roughly double its mass every 50 million years, but only if it can maintain this rate continuously. In reality, accretion is probably episodic. A black hole accretes rapidly when there is a lot of gas in the galactic nucleus, such as after a galaxy merger that funnels gas toward the center. During quieter periods, the accretion rate drops dramatically. Over the lifetime of the universe, about 13.8 billion years, a black hole starting from a seed mass of 100 solar masses and accreting at the Eddington limit could potentially grow to about 100 billion solar masses. But sustained Eddington limited accretion is probably unrealistic, so actual growth is slower. This suggests that mergers play a crucial role in building ultramassive black holes. Holmburg 15A's location at the center of a rich galaxy cluster makes it an ideal environment for black hole growth through mergers. Galaxy clusters are densely populated regions where galaxies frequently collide and merge. Each time a galaxy falls into the cluster center and merges with Holmburg 15A, its central black hole is delivered to Holmburg 15A's core. Initially, the infalling black hole orbits within the merged galaxy, gradually sinking toward the center due to dynamical friction. As it interacts with stars, it loses orbital energy and spirals inward. Eventually, the two black holes, Holmburg 15A's original black hole and the one from the infalling galaxy, form a binary. The binary shrinks as stars interact with it, carrying away energy and angular momentum. When the binary reaches a separation of roughly a light year or less, gravitational wave emission becomes the dominant energy loss mechanism, causing the black holes to spiral together and merge. The resulting black hole has a mass equal to the sum of the two original masses, minus a small amount of mass, converted to gravitational wave energy according to Einstein's E equals mc squared. The number of mergers required to build a 22 billion solar mass black hole depends on the masses of the merging black holes. If Holmburg 15A's black hole grew primarily by merging with other ultramassive black holes in the billion solar mass range, relatively few mergers would be needed, perhaps a dozen or two. But if most of the mergers involve smaller black holes with masses of hundreds of millions of solar masses, many more mergers would be required. The depleted core of Holmburg 15A provides evidence that multiple major mergers have occurred. Each merger involving a massive black hole binary would contribute to excavating the core, ejecting stars and leaving behind a larger stellar deficit. The observed core size of 15,000 light-years is consistent with the black hole mass when compared to other galaxies with depleted cores, suggesting that the core was shaped primarily by the final few major mergers that built most of the black hole's current mass. Gravitational waves from merging supermassive black holes are among the most powerful events in the universe. When two black holes with masses of several billion solar masses spiral together and merge, they emit gravitational waves with a characteristic frequency in the nanohertz range, oscillations with periods of years, rather than the milliseconds seen in stellar mass black hole mergers. These low-frequency gravitational waves cannot be detected by ground-based detectors like LIGO, which are sensitive to much higher frequencies. Instead, astronomers search for them using pulsar timing arrays, networks of precisely monitored millisecond pulsars distributed across the sky. Gravitational waves passing between Earth and these pulsars cause tiny variations in the arrival times of their pulses. By monitoring dozens of pulsars simultaneously over many years, astronomers hope to detect the background hum of gravitational waves from supermassive black hole mergers occurring throughout the universe. Recent results from pulsar timing arrays suggest this background may have been detected, providing the first indirect evidence that supermassive black hole mergers are occurring as theory predicts. galactic cannibalism and the growth of Holmburg. 15A. The enormous size of Holmburg 15A is not solely due to its central black hole. The galaxy itself, with its 2 trillion stars, represents the accumulated mass of dozens, or even hundreds, of smaller galaxies consumed over billions of years. This process, known as galactic cannibalism, is the dominant mechanism by which central cluster galaxies grow to such extreme sizes. When a smaller galaxy ventures too close to Holmburg 15A, tidal forces, differences in gravitational pull across the galaxy's extent, begin to tear it apart. Stars on the near side of the infalling galaxy feel a stronger pull toward Holmburg 15A than stars on the far side. This differential force stretches the galaxy, pulling stars away from its center and creating long tidal tails that can stretch for hundreds of thousands of light years. Eventually, the disrupted galaxy stars are incorporated into Holmburg 15A's outer halo, adding to its total mass. Evidence of past cannibalisms can sometimes be seen in the form of tidal stream, coherent structures of stars tracing the orbits of disrupted galaxies. These streams are visible in nearby galaxies where individual stars can be resolved, but at the distance of Holmburg 15A, such features are extremely difficult to detect. Instead, astronomers look for statistical signatures in the galaxy's stellar population. If Holmburg 15A grew by accreting many smaller galaxies, its outer region should contain a mix of stellar populations with different ages and chemical compositions, reflecting the diverse origins of the accreted stars. Spectroscopic studies that measure the abundances of elements like iron, magnesium, and calcium in different parts of the galaxy can reveal this chemical heterogeneity. Preliminary studies suggest that Holmburg 15A does indeed show variations in stellar populations with radius, consistent with the idea that its outer halo was built up through mergers. The rate of galactic cannibalism in a cluster depends on several factors: the density of galaxies, the relative velocities of galaxies as they move through the cluster, and the efficiency with which tidal forces disrupt infalling galaxies. In Abell 85, the galaxy density is quite high, especially in the central region where Holmburg 15A resides. Over the past several billion years, dozens of galaxies have likely fallen into this region and been consumed. Computer simulations of galaxy cluster evolution show that central galaxies can grow by a factor of 2 to 5 through mergers, with most of the growth occurring in the last few billion years. This matches the observed properties of Holmburg 15A, which is significantly more massive than a typical elliptical galaxy, but not implausibly so given its cluster environment. An interesting consequence of galactic cannibalism is the formation of a diffuse intracluster light, stars that are not bound to any individual galaxy, but instead orbit in the general gravitational field of the cluster as a whole. When a galaxy is disrupted by tidal forces, some of its stars are added to the central galaxy, but others are flung into the space between galaxies. Over time, these stars accumulate to form a diffuse glow that fills the cluster. Observations of rich galaxy clusters have detected this intracluster light, which can contain up to 50% of the cluster's total stellar mass in extreme cases. In Abell 85, intracluster light has been observed, indicating that the process of galactic disruption has been at work. Some of the stars that were once part of now destroyed galaxies may be contributing to this diffuse component rather than being incorporated into Holmburg 15A itself. The relationship between Holmburg 15A and the other galaxies in Abell 85 is also instructive. As the dominant central galaxy, Holmburg 15A sits nearly at rest in the cluster's center, while smaller galaxies orbit around it at high speed. Typical velocities within the cluster are around 800 to 1,000 kilometers per second, fast enough that a galaxy could cross the entire cluster in a few 100 million years. These high velocities result from the cluster's deep gravitational potential well. When two galaxies approach each other at such high speeds, they typically do not merge on the first pass. Instead, they fly past each other, pulled off course by their mutual gravitational attraction but not captured. However, during this close encounter, both galaxies lose orbital energy through tidal interactions and dynamical friction, causing them to fall back together on subsequent orbits. After several passes, the galaxies eventually merge. This process can take billions of years for the largest galaxies, but the end result is always the same. The smaller galaxy is destroyed, and its stars are added to the larger one. Holmburg 15A's smooth featureless appearance indicates that it has not experienced a major merger recently, at least not within the past billion years or so. Major mergers leave behind observable disturbances, shells, ripples, tidal tails, and asymmetries in the light distribution. These features fade over time as the stellar orbits phase mix and settle into a smooth equilibrium, but they remain visible for a billion years or more. The fact that Holmburg 15A appears so smooth suggests that its last major merger occurred in the relatively distant past, giving the galaxy time to relax and settle. This is consistent with the idea that Holmburg 15A has been sitting at the center of Abell 85 for a long time, slowly growing through the accretion of smaller galaxies, but not experiencing the violent major mergers that characterized its earlier history. The X-ray halo, evidence of AGN feedback. Holmburg 15A is not just a galaxy, it is embedded in a vast halo of hot gas, this intracluster medium, as it is called, containing more mass in gas than in all the galaxies in the cluster combined. The gas is heated to temperatures of tens of millions of degrees, hot enough that it emits X-rays. These X-rays can be detected by space-based telescopes like Chandra and XMM Newton, which have mapped the distribution and temperature of the gas throughout Abell 85. What these observations reveal is a complex interplay between the galaxy and its surroundings, mediated by the supermassive black hole at Holmburg 15A's core. This interplay, known as AGN feedback, is one of the most important processes shaping the evolution of massive galaxies. A GN stands for active galactic nucleus, a term referring to the energetic emission produced when a supermassive black hole actively accretes matter. As gas falls toward the black hole, it forms a swirling accretion disk where gravitational energy is converted to heat through friction and magnetic interaction. The inner regions of this disk become so hot that they emit copious amounts of high-energy radiation, including X-rays and ultraviolet light. In some cases, the accreting black hole also launches powerful jets of relativistic plasma, particles accelerated to nearly the speed of light, that shoot outward perpendicular to the accretion disk. These jets can extend for millions of light years, plowing through the surrounding gas and depositing enormous amounts of energy. Even when jets are not present, the radiation from the accretion disk can heat nearby gas, driving winds that carry material away from the galaxy. X-ray observations of Holmburg 15A reveal clear signs of AGN feedback. The distribution of hot gas around the galaxy is not smooth. Instead, there are cavities, regions where the gas density is significantly lower than average. These cavities are typically interpreted as bubbles blown by jets or winds from the central black hole. As the jets push through the hot gas, they displace it, creating low-density voids surrounded by shells of compressed, hotter gas. The size and shape of these cavities can be used to estimate how much energy the black hole has injected into the surrounding medium. In Holmburg 15A's case, the cavities are relatively small and subtle compared to those seen in some other central cluster galaxies, suggesting that the black hole is not currently in a highly active state. However, the presence of cavities at all indicates that AGN activity has occurred in the relatively recent past. The importance of AGN feedback extends far beyond simply heating the intracluster medium. Without feedback, the hot gas in galaxy clusters would cool and condense, falling toward the center of the cluster and forming enormous amounts of new stars. Simple calculations show that the cooling time for the gas in the cores of galaxy clusters is often less than 1 billion years, much shorter than the age of the cluster. If cooling proceeded unhindered, we would expect to see massive central galaxies like Holmburg 15A forming stars at rates of hundreds or even thousands of solar masses per year, producing young, blue stellar populations. Yet observations show exactly the opposite. Central cluster galaxies like Holmburg 15A are red and dead, dominated by old stars with very little ongoing star formation. The star formation rate in Holmburg 15A is essentially zero. This is the classic cooling flow problem, and AGN feedback is the solution. By injecting energy into the hot gas, the supermassive black hole prevents it from cooling too quickly. The jets and winds from the AGN stir the gas, mixing hotter material from the outer regions into the cool core and maintaining the gas at high temperatures. This negative feedback loop operates as follows. When the gas begins to cool and fall toward the black hole, some of it is accreted, increasing the black hole's accretion rate. This causes the AGN to become more luminous, launching more powerful jets and winds. These outflows deposit energy in the surrounding gas, heating it and halting the cooling. As a result, the accretion rate drops, the AGN becomes less active, and the feedback weakens. The gas begins to cool again, restarting the cycle. This self-regulating mechanism maintains a balance between cooling and heating, preventing runaway star formation, while allowing the black hole to grow slowly over cosmic time. The total energy budget involved in AGN feedback is staggering. The mechanical energy injected by jets over the lifetime of a cluster can exceed 10 to the 60 ergs, equivalent to the energy released by millions of supernova explosions. This energy is sufficient to unbind large quantities of gas from the galaxy's gravitational potential, well expelling it into intergalactic space. Observations of galaxy clusters show that AGN feedback is remarkably effective at regulating star formation in the most massive galaxies. Holmburg 15A's lack of significant star formation despite its enormous gas reservoir is direct evidence of this process at work. The black hole has essentially shut down star formation in the galaxy's core, preventing the galaxy from converting its gas supply into new stars and keeping it red and quiescent. The future: gravitational waves and mergers. Looking ahead, the study of ultramassive black holes like the one in Holmberg 15A is poised to enter a transformative era driven by gravitational wave astronomy. While current detectors such as LIGO have revolutionized our understanding of stellar mass black hole mergers, they are insensitive to the much lower frequency gravitational waves produced by supermassive and ultramassive black hole binaries. That gap will be filled by the Laser Interferometer Space Antenna, or LISA, a planned space-based observatory designed to detect gravitational waves in the millihertz frequency range. Operating far from Earth's seismic noise, LISA will be capable of observing black hole mergers involving masses from millions to billions of times that of the Sun, precisely the regime occupied by the most extreme galaxies in the universe. Although the black hole at the center of Holmburg 15A is not currently part of a close binary system, its long-term future makes it a compelling candidate for such events. As the dominant galaxy in the Abell 85 cluster, Holmburg 15A will continue to grow through mergers within falling galaxies, many of which bring their own central black holes. Over billions of years, dynamical friction will cause these black holes to sink toward the center, eventually forming bound binaries that will spiral together and merge. When this occurs, the resulting gravitational wave signal will carry detailed information about the masses, spins, and orbital dynamics of the merging black holes. Detecting such mergers will allow astronomers to test general relativity in its most extreme regime, where space-time is violently distorted and classical physics fails entirely. At the same time, these observations will illuminate the role of black holes in shaping galaxy evolution. Ultramassive black holes like the one in Holmburg 15A represent the final products of hierarchical growth, preserving a record of countless mergers. By studying them, astronomers gain insight into how the largest structures in the universe assembled and how gravity governs the cosmos at its most extreme scales. Gravitational wave observations of supermassive black hole mergers will provide crucial tests of general relativity in the strong field regime, regions of space-time where gravity is so intense that Newtonian physics breaks down completely and only Einstein's theory remains valid. Black hole mergers involve the collision and coalescence of event horizons, processes that are predicted by general relativity but have never been directly observed. The gravitational waveforms emitted during the merger encode information about the properties of the black holes, including their masses, spins, and the amount of energy radiated away. By comparing the observed waveforms to theoretical predictions, astronomers can test whether general relativity accurately describes these extreme events or if deviations from the theory become apparent at such high energies and densities. Another reason to study ultramassive black holes, like the one in Holmburg 15A, is their potential connection to the growth of structure in the universe. The distribution of black hole masses across cosmic time provides insights into how galaxies form and evolve. In the early universe, galaxies were smaller and less massive, and their black holes were correspondingly smaller. Over billions of years, hierarchical merging built ever larger galaxies and ever larger black holes. The most massive black holes we see today, like the one in Holmburg 15A, are the end products of this hierarchical growth. By studying the properties of ultramassive black holes and the galaxies that host them, astronomers can reconstruct the merger history that led to their formation. This, in turn, provides a fossil record of galaxy assembly over cosmic time. The relationship between black hole mass and the properties of the host galaxy, encapsulated in scaling relations like the m-sigma relation and the correlation between black hole mass and bulge mass, suggests that black holes and galaxies co-evolve. Supermassive black holes do not grow in isolation. Their growth is intimately tied to the growth of their host galaxies through processes like mergers and AGN feedback. Understanding this co-evolution requires studying black holes across a wide range of masses and host galaxy types. Ultramassive black holes like the one in Holmburg 15A represent the extreme end of this distribution, where the scaling relations may break down, or where new physical processes become important. By measuring their properties precisely, astronomers can refine theoretical models and improve our understanding of the fundamental physics governing black hole and galaxy formation. Looking forward, one of the most promising frontiers in the study of ultramassive black holes is gravitational wave astronomy. Future detectors will allow astronomers to observe black hole mergers not through light, but through ripples in space-time itself. This represents a fundamentally new way of studying the universe, especially for objects that are otherwise difficult or impossible to observe electromagnetically. A key instrument in this effort will be the Laser Interferometer Space Antenna, or LISA. Unlike ground-based detectors such as LIGO, which are sensitive to high-frequency gravitational waves from stellar mass black holes, LISA will operate in the millihertz frequency range. This makes it uniquely suited to detecting mergers involving black holes with masses of millions to billions of times that of the Sun. Scheduled for launch in the 2030s, LISA will be capable of tracking supermassive black hole binaries for months or even years before they merge. While a merger involving the black hole in Holmburg 15A is unlikely in the near future, its environment makes such an event inevitable on cosmic timescales. As the central galaxy of the Abell 85 cluster, Holmburg 15A will continue to accrete smaller galaxies, many of which contain their own massive black holes. Over time, these black holes will sink toward the center and eventually form gravitationally bound binaries that can merge and emit powerful gravitational waves. Observations of these mergers will provide direct tests of general relativity in the strongest gravitational fields known. The detailed shape of the gravitational wave signal encodes information about black hole masses, spins, and orbital dynamics. Comparing these signals to theoretical predictions will allow physicists to determine whether Einstein's theory holds under such extreme conditions. Ultramassive black holes also offer critical insight into the growth of cosmic structure. Objects like the one in Holmburg 15A represent the endpoints of hierarchical galaxy assembly. By studying them, astronomers can reconstruct the merger history of galaxy clusters and better understand how the larger structures in the universe came to be. Comparisons. Other ultramassive black holes. Holmburg 15A's black hole is extraordinary, but it is not alone. Several other galaxies are known to host ultramassive black holes with masses exceeding 10 billion solar masses, and comparing these systems provides valuable insights into the diversity of black hole growth pathways. One of the most famous examples is NGC 4889, the brightest cluster galaxy in the Coma cluster. NGC 4889's black hole was measured in 2011 and found to have a mass of approximately 21 billion solar masses, comparable to Holmburg 15A's black hole. Like Holmburg 15A, NGC 4889 sits at the center of a rich galaxy cluster and shows evidence of a depleted core, suggesting a similar formation history involving multiple mergers. The Coma cluster is one of the richest and most massive clusters in the nearby universe, making it an ideal environment for building ultramassive black holes through hierarchical merging. Another notable example is the black hole in NGC 1600, a giant elliptical galaxy located in a relatively poor group rather than a rich cluster. Despite the less dense environment, NGC 1600's black hole has a mass of about 17 billion solar masses. The existence of such a massive black hole in a group environment is somewhat surprising, as groups typically have fewer galaxies and lower merger rates than clusters. One possibility is that NGC 1600 experienced an unusually large number of major mergers in its early history, building up both its stellar mass and its black hole mass before settling into the group environment. Alternatively, the galaxy may have been part of a denser environment in the past and later fell into a lower density region. The NGC 1600 black hole also shows evidence of being slightly offset from the galaxy's center, possibly indicating a recent merger that has not yet fully relaxed. TON 618, a distant quasar, hosts one of the most massive black holes known, with estimates ranging from 40 to 66 billion solar masses. However, TON 618 is much farther away than Holmburg. 15A, it lies at a redshift of 2.2, meaning we see it as it appeared more than 10 billion years ago, when the universe was much younger. The black hole is actively accreting at an enormous rate, powering a quasar so bright it outshines its entire host galaxy. The existence of such a massive black hole so early in the universe's history poses challenges for theories of black hole growth. To reach 40 to 66 billion solar masses by a redshift of 2.2 requires either continuous accretion at or above the Eddington limit for billions of years, or the formation of unusually massive seed black holes in the early universe. Patient 618's black hole is likely still growing, whereas Holmberg 15A's black hole is probably in a quiescent phase, having already consumed most of the available gas in its vicinity. Another interesting comparison is Phoenix A, a galaxy at the center of the Phoenix cluster. Phoenix A's black hole is estimated to have a mass of around 100 billion solar masses, potentially making it the most massive black hole known if the measurement is correct. However, this estimate is more uncertain than those for Holmberg 15A or NGC 4889 because it relies on indirect methods rather than direct dynamical measurements. The Phoenix cluster is unusual in that it shows evidence of extremely high star formation rates despite being a mature cluster, suggesting that AGN feedback has not yet fully shut down cooling flows. The massive central black hole in Phoenix A may be in a transitional phase, growing rapidly through accretion of cooling gas, while simultaneously expelling some of that gas through feedback. Comparing Phoenix A to Holmberg 15A highlights the diversity of evolutionary states among ultramassive black holes. IC1101, often cited as one of the largest galaxies in the universe, is another supergiant elliptical located in the Abell 2029 cluster. Early estimates suggested its black hole might have a mass exceeding 40 billion solar masses, but more recent measurements have revised this downward to around 10 billion solar masses. This revision underscores the difficulty of measuring black hole masses accurately, especially for the most massive systems where uncertainties in the galaxy's structure and dynamics can significantly affect the results. IC1101's galaxy is physically larger than Holmberg 15A, with a stellar halo extending over 6 million light-years, but its black hole is less massive. This suggests that black hole mass and galaxy size, while correlated on average, do not always scale linearly. Some galaxies may grow primarily through dry mergers with little gas involved, which add to the galaxy's stellar mass but do not significantly feed the central black hole. The distribution of ultramassive black holes across the universe is not random. They are almost exclusively found in the most massive elliptical galaxies, particularly those located at the centers of galaxy clusters or in dense groups. This environmental dependence reflects the fact that ultramassive black holes require special conditions to form, either very efficient accretion in the early universe or multiple major mergers over cosmic time. The hierarchical model of structure formation predicts that the most massive structures in the universe form through the successive merging of smaller structures, and ultramassive black holes are a natural outcome of this process. As observational techniques improve and more galaxies are surveyed with high-quality spectroscopy, the census of ultramassive black holes will grow, allowing astronomers to better understand the extreme end of the black hole mass function. Stellar dynamics and orbital structure. The motion of stars within Holmburg 15A is governed by a complex interplay of gravitational forces from the black hole, the stellar mass of the galaxy, and the dark matter halo. Unlike stars in spiral galaxies, which often follow orderly circular orbits in a thin disk, stars in elliptical galaxies like Holmburg 15A move on a wide variety of orbital trajectories. Some stars follow nearly radial orbits, plunging in toward the center and then back out to large distances. Others follow more circular paths, staying at roughly constant radius. Still others move on complex three-dimensional orbits that loop and weave through the galaxy. The collective motion of all these stars determines the galaxy's shape and the observed velocity field that astronomers measure through spectroscopy. The key quantity used to characterize stellar motion in elliptical galaxies is the velocity dispersion, which measures the spread in stellar velocities at any given location. If all stars at a particular radius were moving with exactly the same speed in exactly the same direction, the velocity dispersion would be zero. In reality, stars have a wide range of velocities, and the velocity dispersion quantifies this randomness. In Holmburg 15A, the velocity dispersion in the outer parts of the galaxy is approximately 300 to 350 kilometers per second. This is quite high compared to smaller elliptical galaxies, reflecting the deep gravitational potential well of this massive galaxy. Closer to the center, within the depleted core, the velocity dispersion drops slightly, a feature related to the removal of stars during core scouring. The velocity field in Holmburg 15A also shows evidence of slow rotation. The galaxy rotates about an axis, with stars on one side of the axis moving toward us and stars on the other side moving away. This creates a systematic pattern in the Doppler-shifted spectral lines. However, the rotation velocity, about 20 kilometers per second, is much smaller than the velocity dispersion. This means the galaxy is dispersion-supported rather than rotation-supported. In dispersion-supported systems, the random motions of stars are much larger than their organized rotational motion, and it is the pressure from these random motions that prevents the galaxy from collapsing under its own gravity. This is in contrast to spiral galaxies, which are rotation-supported. Their orderly rotation provides the centrifugal force needed to balance gravity. The misalignment between the kinematic axis and the photometric major axis in Holmburg 15A indicates that the galaxy is triaxial. In an axisymmetric galaxy, the kinematic and photometric axes would align, because the galaxy's rotation would naturally follow its elongation. The fact that they do not align means the galaxy has three unequal principal axes. Stars in triaxial galaxies move on orbits that sample all three dimensions, and the viewing angle matters significantly. Depending on how the galaxy is oriented relative to our line of sight, the observed velocity field can appear very different, even if the intrinsic orbital structure is the same. Modeling triaxial galaxies is therefore more complex than modeling axisymmetric ones, requiring more sophisticated numerical techniques like the Tri-OS code used in the 2025 study that revised Holmburg 15A's black hole mass. One particularly interesting class of orbits in triaxial galaxies is box orbits. These orbits pass through the center of the galaxy, oscillating back and forth along each of the three principal axes. Box orbits can support a triaxial shape because they preferentially populate regions along the galaxy's major axis. However, box orbits have a problem. They pass arbitrarily close to the galactic center, where the black hole resides. If the black hole mass is large enough, stars on box orbits will be strongly perturbed or even scattered onto completely different orbits when they approach the black hole. This process, known as the chaotic destruction of box orbits, tends to make the galaxy more axisymmetric over time. The fact that Holmburg 15A remains triaxial suggests that either the black hole mass is not yet large enough to have completely destroyed the box orbits, or the galaxy has experienced a relatively recent merger that replenished the box orbit population. The orbital structure of stars in the depleted core is especially interesting because these stars have survived the core scouring process. During a black hole binary merger, stars that venture too close to the binary are ejected at high velocities, removing them from the core. The stars that remain are those on orbits that avoid close encounters with the binary. Over time, this selective ejection process changes the orbital distribution in the core, preferentially removing certain types of orbits while leaving others. The net result is a core with a lower stellar density and a different mix of orbital types compared to the original galaxy. By measuring the detailed velocity field in the depleted core, astronomers can learn about the efficiency of core scouring and the properties of the black hole binary that created the core. The stellar motions in Holmburg 15A reveal a galaxy dominated by random, three-dimensional orbits rather than orderly rotation. High-velocity dispersion reflects its deep gravitational potential, while weak rotation confirms it is dispersion-supported. Misalignment between photometric and kinematic axes shows the galaxy is triaxial, requiring complex orbital structures such as box orbits. The depleted core preserves signatures of past black hole mergers, where gravitational interactions reshaped stellar orbits through core scouring. The temperature and chemistry of Holmburg 15A's stars. The stars in Holmburg 15A are ancient, formed billions of years ago in smaller galaxies that have since merged to create the supergiant elliptical we see today. Determining the ages of these stars requires analyzing their light spectra to identify the chemical elements present in their atmospheres. Stars form from clouds of gas, and the chemical composition of that gas reflects the history of nucleosynthesis, the production of elements through nuclear fusion in earlier generations of stars. The first stars in the universe contained only hydrogen and helium, the primordial elements created in the Big Bang. These stars fused hydrogen into helium in their cores, and the most massive ones eventually exploded as supernovae, creating heavier elements like carbon, oxygen, iron, and nickel. Subsequent generations of stars incorporated these metals into their composition, with each generation becoming progressively more metal-rich. Astronomers use the term metallicity to describe the abundance of elements heavier than hydrogen and helium in a star's composition. High metallicity stars form from gas that had been enriched by many previous generations of star formation and supernovae. Low metallicity stars, conversely, form from gas that had undergone relatively little chemical enrichment. By measuring the metallicity of stars in Holmburg 15A, astronomers can infer when those stars formed and in what environment. The galaxy's stars show a range of metallicities, with the most metal-rich stars likely formed in the centers of massive galaxies before those galaxies merged into Holmburg 15A. The metal-poor stars, on the other hand, may have formed in smaller satellite galaxies that were subsequently accreted. The integrated spectrum of Holmburg 15A, the combined light from all the stars in the galaxy, shows strong absorption lines from elements like magnesium, iron, and calcium. These absorption lines are created when light from the stellar photospheres passes through the cooler outer layers of the star's atmospheres, where atoms of these elements absorb specific wavelengths. The strength of these absorption lines provides information about the abundance of each element and the temperature of the stellar atmospheres. For Holmburg 15A, the spectrum is typical of an old stellar population dominated by K and M giant stars. Cool, evolved stars that have exhausted the hydrogen in their cores and expanded to become red giants. These stars produce a red overall color for the galaxy and strong absorption lines from metals. One particularly informative spectral feature is the alpha to iron ratio, often denoted as alpha over Phi. Alpha elements include oxygen, neon, magnesium, silicon, sulfur, and calcium, which are produced primarily in Type II supernovae, the explosions of massive stars. Iron, on the other hand, is produced in significant quantities by Type Ia supernovae, the thermonuclear explosions of white dwarf stars in binary systems. Type II supernovae occur quickly after a burst of star formation, since massive stars have short lifetimes of only a few million years. Type Ia supernovae, in contrast, have a delay time distribution, with some exploding quickly, but many occurring hundreds of millions or even billions of years after the initial starburst. As a result, a stellar population that forms rapidly and then stops will initially have a high alpha to iron ratio, which gradually decreases as Type Ia supernovae contribute more iron. Measurements of the alpha to iron ratio in Holmburg 15A show that the stars are alpha enhanced, meaning they have a higher ratio of alpha elements to iron than the Sun. This indicates that the stars formed in a short, intense burst of star formation, followed by rapid quenching, the cessation of star formation. This is consistent with the formation scenario for massive elliptical galaxies, which are thought to have formed most of their stars in the early universe during a period of vigorous star formation, and then evolved passively afterward. The merger events that assembled Holmberg 15A did not trigger significant new star formation because the merging galaxies were gas-poor by the time they collided. Instead, the mergers simply rearranged the existing old stellar populations, combining them into an ever larger galaxy without adding significant numbers of young stars. The lack of young stars in Holmberg 15A is confirmed by the absence of blue or ultraviolet light in its spectrum. Young, massive stars are hot and blue, producing copious ultraviolet radiation. The fact that Holmberg 15A's spectrum is dominated by red and infrared light indicates that the galaxy has not formed significant numbers of massive stars for at least several billion years. This places Holmberg 15A firmly in the category of red and dead galaxies, systems that have exhausted their gas supplies and are no longer actively forming stars. The only star formation that occurs in such galaxies is at extremely low rates, producing perhaps a few solar masses of new stars per year at most. This stands in stark contrast to star-forming galaxies like the Milky Way, which produce several solar masses of new stars every year. The stellar population of Holmberg 15A is uniformly old, formed during brief, intense episodes of star formation early in the universe's history. Spectroscopic measurements show high metallicity and strong absorption lines from elements such as magnesium, iron, and calcium, indicating multiple generations of prior stellar enrichment. The stars are alpha enhanced, revealing rapid formation followed by early quenching before Type Ia supernovae added significant iron. The galaxy's red spectrum and lack of ultraviolet emission confirm the absence of young stars, consistent with a gas-poor, passively evolving supergiant elliptical assembled through mergers rather than ongoing star formation. The intracluster medium and cooling flows. The space between galaxies in the Abell 85 cluster is not empty. It is filled with an extremely tenuous but very hot gas, the intracluster medium, which emits X-rays and provides a major component of the cluster's baryonic mass. This gas reaches temperatures of 30 to 80 million Kelvin, hot enough that it is fully ionized. All the electrons have been stripped from their atoms. At such temperatures, the gas emits X-rays through a process called thermal Bremsstrahlung, in which electrons scatter off ions and emit photons. The total X-ray luminosity of Abell 85 is enormous, around 10 to the 44th ergs per second, making it one of the brightest X-ray clusters in the nearby universe. This X-ray emission provides a powerful diagnostic tool for studying the cluster's properties, including its mass distribution, temperature structure, and dynamical state. The origin of the hot intracluster medium is tied to the process of structure formation in the universe. As matter collapses under gravity to form galaxies and galaxy clusters, gravitational potential energy is converted to kinetic energy. Gas falling into the cluster's gravitational potential well heats up through a process called shock heating. When gas crosses the accretion shock at the edge of the cluster, it is suddenly compressed and heated to millions of degrees. This shock-heated gas then fills the cluster, maintaining its high temperature through subsequent gravitational interactions. Additional heating can come from supernova explosions in cluster galaxies, AGN feedback from central black holes, and the kinetic energy released during galaxy mergers. The result is a vast reservoir of hot gas that represents a significant fraction of the cluster's total baryonic mass. In many clusters, there is more mass in hot gas than in all the stars in all the galaxies combined. X-ray observations of Abell 85 reveal a complex temperature structure. The gas in the very center of the cluster, surrounding Holmburg 15A, is slightly cooler than the gas farther out. This temperature drop is evidence of a cooling flow, a process in which the gas in the cluster core radiates away energy through X-ray emission faster than it can be replenished by heating. As the gas cools, its density increases, and it should eventually condense out of the hot phase and fall toward the center of the cluster. Simple calculations based on the observed X-ray luminosity suggest that hundreds of solar masses of gas per year should be cooling and condensing in the cores of clusters like Abell 85. This condensed gas would then be available to form new stars or feed the central black hole. However, as mentioned earlier, observations do not show the expected consequences of strong cooling flows. Holmburg 15A is not forming hundreds of solar masses of stars per year, and the expected signatures of large amounts of cool gas, such as strong emission lines from ionized gas or large quantities of molecular gas detected in radio observations, are either weak or absent. This discrepancy is the cooling flow problem, and it strongly suggests that some heating mechanism is counteracting the radiative cooling. AGN feedback from the supermassive black hole in Holmburg 15A is the leading candidate for this heating mechanism. By injecting energy into the intracluster medium through jets and winds, the black hole can offset the radiative cooling and maintain the gas at high temperatures. The balance between cooling and heating in cluster cores is delicate and probably time variable. When the cooling rate exceeds the heating rate, gas begins to condense and fall toward the black hole, increasing the accretion rate. This triggers an outburst of AGN activity, which heats the gas and halts the cooling. The AGN activity then declines as the fuel supply diminishes, allowing cooling to resume. This cycle repeats over timescales of hundreds of millions of years, producing the X-ray cavities and other structures observed in the intracluster medium. In Abell 85, the presence of relatively small X-ray cavities near Holmburg 15A suggests that the cluster is currently in a relatively quiescent phase, with only moderate AGN activity. The cavities visible in X-ray images are probably the remnants of past outbursts that occurred tens or hundreds of millions of years ago. The interaction between the intracluster medium and Holmburg 15A extends beyond just AGN feedback. The hot gas exerts a pressure on the outer parts of the galaxy, preventing the galaxy from extending indefinitely into space. In less massive galaxies located in the outskirts of clusters, this pressure can even strip gas from the galaxy through ram pressure stripping, removing the raw material needed for star formation. Holmburg 15A, being at the center of the cluster and extremely massive, is not subject to ram pressure stripping. However, the surrounding hot gas does create a confining pressure that affects the distribution of any remaining cold gas in the galaxy. Observations at radio wavelengths have detected small amounts of molecular gas near the center of Holmburg 15A, probably the remnants of cooling flows or gas left over from past mergers. The total mass of cold gas is small, less than 1 billion solar masses, and it is not forming stars at any significant rate, consistent with the overall quiescent nature of the galaxy. The Schwarzschild radius and event horizon. At the heart of Holmburg 15. A lies the event horizon of the ultramassive black hole, the boundary beyond which nothing can escape. For a black hole with a mass of 22 billion solar masses, the Schwarzschild radius, the radius of the event horizon for a non-rotating black hole, is approximately 65 billion kilometers. This is an almost incomprehensibly large distance. To put it in perspective, the orbit of Neptune around the Sun has a radius of about 4.5 billion kilometers, making the black hole's event horizon roughly 15 times larger than Neptune's orbit. Light itself, travelling at 300,000 kilometers per second, would take about 60 hours to traverse the diameter of the event horizon. Inside this boundary, space-time is so severely curved that all future paths lead inevitably toward the singularity at the centre, regardless of how much energy an object expends trying to escape. The properties of the event horizon are determined entirely by the black hole's mass, spin, and electric charge, according to the no-hair theorem of general relativity. This theorem states that stationary black holes are characterized by only three quantities: mass, angular momentum, and electric charge. All other information about the matter that formed the black hole, its composition, the arrangement of its atoms, the detailed structure of the infalling material, is lost once the matter crosses the event horizon. For astrophysical black holes, electric charge is negligible, because any significant charge would be quickly neutralized by attracting opposite charges from the surrounding plasma. This leaves only mass and spin as the relevant parameters. The Holmburg 15A black hole's mass has been measured, but its spin remains unknown. Black hole spin is an important quantity because it affects the structure of space-time near the event horizon and determines how much energy can be extracted from the black hole's rotational energy. A maximally spinning black hole, one rotating at the fastest rate allowed by general relativity, has an angular momentum parameter of equals 1. Such a black hole has an ergosphere, a region outside the event horizon where space-time itself is dragged around by the black hole's rotation. Objects in the ergosphere are forced to rotate in the same direction as the black hole, regardless of their own motion. Energy can be extracted from a spinning black hole through the Penrose process, or, more realistically in astrophysical contexts, through the Blandford-Znajek mechanism, in which magnetic field lines threading the ergosphere extract rotational energy and channel it into relativistic jets. Measuring the spin of supermassive black holes is challenging. One method involves observing the X-ray emission from the innermost regions of the accretion disk, where relativistic effects shape the spectral features in characteristic ways. The iron K-alpha emission line, produced when iron atoms in the accretion disk are ionized by high-energy photons, is particularly useful. The line is broadened and skewed by Doppler shifts, gravitational redshift, and light bending near the black hole. The exact shape of this distorted line profile depends on the black hole's spin, allowing astronomers to infer the spin parameter from high-quality X-ray spectra. However, this technique requires the black hole to be actively accreting, and Holmberg 15A's black hole is currently quiescent, producing negligible X-ray emission. As a result, its spin cannot be measured using this method at present. Another approach to estimating black hole spin involves theoretical arguments based on the black hole's growth history. If the black hole grew primarily through coherent accretion, gas falling in from a preferred direction over long periods, its spin would gradually increase toward the maximum value. Coherent accretion naturally spins up the black hole because the infalling gas carries angular momentum. On the other hand, if the black hole grew primarily through mergers with other black holes entering from random directions, its spin would remain relatively low. Each merger adds angular momentum, but if the directions are random, the spin increases more slowly and can even decrease if a merger involves black holes with opposite spin directions. Given that Holmburg 15A likely grew through multiple major mergers, its black hole spin is probably moderate rather than maximal. But without direct measurements, this remains speculative. The event horizon itself is not a physical surface. It is simply a mathematical boundary in space-time. defined as the location where the escape velocity equals the speed of light. An observer falling toward a black hole would not notice anything special upon crossing the event horizon, at least not immediately. However, the tidal forces near the event horizon of an ultramassive black hole like Holmburg 15A's are relatively weak compared to those near a stellar mass black hole. Tidal forces arise because gravity is stronger on the side of an object closer to the black hole than on the far side. For a stellar mass black hole with a mass of 10 solar masses, the tidal forces at the event horizon are strong enough to rip apart any ordinary object, a process colourfully termed spaghettification. But for an ultramassive black hole, the event horizon is so large that the tidal forces there are surprisingly mild. A human falling toward Holmburg 15A's black hole would survive crossing the event horizon intact, only to be torn apart later as they approached the singularity. The singularity and quantum gravity. At the very centre of the black hole, general relativity predicts the existence of a singularity, a point where space-time curvature becomes infinite and the known laws of physics break down. In the Schwarzschild solution for a non-rotating black hole, the singularity is a single point at the centre. For a rotating black hole described by the Kerr solution, the singularity takes the form of a ring. The nature of the singularity is one of the greatest unsolved problems in theoretical physics, because it represents a regime where both general relativity and quantum mechanics are important, yet we do not have a complete theory of quantum gravity to describe it. At the singularity, densities and curvatures become arbitrarily large, and the smooth space-time of general relativity gives way to quantum fluctuations that should, in principle, be described by a theory we do not yet possess. Several approaches to quantum gravity have been proposed, including string theory, loop quantum gravity, and asymptotic safety. String theory posits that the fundamental constituents of the universe are not point particles but tiny, vibrating strings. In this framework, singularities might be resolved by the extended nature of strings, which smear out the point-like concentration of energy that characterizes a classical singularity. Loop quantum gravity, another leading approach, attempts to quantize space-time itself, suggesting that space and time are made of discrete units at the smaller scales. This discretization could prevent the formation of true singularities by imposing a minimum length scale below which space-time cannot be further subdivided. Asymptotic safety proposes that gravity becomes well-behaved at high energies due to the influence of quantum corrections, potentially smoothing out singularities. Despite these theoretical efforts, we have no direct observational evidence to guide us in understanding singularities because they are hidden behind event horizons. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that all singularities in the universe are clothed by event horizons, preventing them from being visible to outside observers. This hypothesis has never been proven rigorously, and there are known solutions to Einstein's equations that contain naked singularities, singularities without event horizons. However, these solutions require exotic conditions that probably do not occur in nature. The black holes we observe, including the ultramassive one in Holmburg 15A, appear to obey cosmic censorship, with their singularities safely hidden from view. One of the most intriguing aspects of black holes is the information paradox, which arises from the conflict between general relativity and quantum mechanics. According to classical general relativity, anything that falls into a black hole is lost forever, disappearing behind the event horizon. But quantum mechanics insists that information cannot be destroyed. This leads to a paradox. If a black hole forms from matter with certain quantum information and then evaporates through Hawking radiation, where does the information go? Does it escape in the radiation? Is it stored somehow in the structure of the event horizon, or is it truly lost? The resolution of this paradox is one of the central goals of quantum gravity research. Stephen Hawking's discovery of black hole radiation, now called Hawking radiation, introduced quantum effects into the study of black holes. Hawking showed that black holes are not completely black, but emit radiation due to quantum effects near the event horizon. virtual particle-antiparticle pairs that spontaneously form in empty space can be separated by the black hole's gravity, with one particle falling in while the other escapes. The escaping particles constitute a radiation field that carries away energy, causing the black hole to slowly evaporate. For stellar mass black holes, this process is extraordinarily slow, taking longer than the current age of the universe to have any measurable effect. For an ultramassive black hole like Holmburg 15A's, the evaporation timescale is incomprehensibly long, on the order of 10 to the 100 years, far longer than the expected lifetime of stars or even protons. The temperature of Hawking radiation is inversely proportional to the black hole's mass. More massive black holes have lower temperatures. For Holmburg 15A's black hole, the Hawking temperature is about 1/1,000,000th of a Kelvin, far colder than the cosmic microwave background radiation that permeates the universe. This means the black hole is actually absorbing more energy from the cosmic microwave background than it radiates through Hawking radiation, causing it to grow rather than shrink. Only in the extremely distant future, after the universe has expanded and cooled to temperatures below the black hole's Hawking temperature, would the black hole begin to lose mass. At that point, the evaporation process would accelerate exponentially, with the black hole becoming hotter as it gets smaller, eventually exploding in a final burst of radiation. However, this will not occur for an unimaginably long time, far exceeding any conventional notion of the future. At a black hole's center, general relativity predicts a singularity where space-time curvature becomes infinite and known physics fails. Resolving this requires a theory of quantum gravity, with candidates such as string theory, loop quantum gravity, and asymptotic safety proposing mechanisms that could eliminate true singularities. These regions remain unobservable, likely hidden by event horizons under the cosmic censorship hypothesis. Quantum effects introduce further puzzles, including the black hole information paradox. Hawking radiation causes black holes to evaporate, but for ultramassive black holes like Holmburg 15A's, this process is extraordinarily slow, occurring only in the unimaginably distant future. The gravitational recoil phenomenon. When two supermassive black holes merge, the resulting system does not necessarily remain at the center of the galaxy. The emission of gravitational waves during the merger is not perfectly symmetric, and this asymmetry can impart a kick to the newly formed black hole, sending it recoiling through space. This gravitational recoil phenomenon arises from the conservation of momentum. If more gravitational wave energy is emitted in one direction than another, the black hole must move in the opposite direction to balance the momentum. The magnitude of this kick depends on several factors, including the mass ratio of the merging black holes, their spins, and the orientation of those spins relative to the orbital plane. For non-spinning black holes with unequal masses, the maximum recoil velocity is relatively modest, around 175 kilometers per second, for a mass ratio of about 5:1. However, when the black holes have significant spins, particularly spins aligned in the orbital plane, the recoil velocities can be much larger. Numerical relativity simulations have shown that under optimal conditions, two equal mass black holes with spins aligned in the orbital plane but pointing in opposite directions, the recoil velocity can reach up to 5,000 kilometers per second. This is far above the escape velocity of even the most massive galaxies, meaning the merged black hole could be ejected entirely from its host galaxy. Such extreme kicks are rare because they require a specific configuration of spins, but they are theoretically possible. More commonly, recoil velocities of a few hundred kilometers per second are expected, which would displace the black hole from the galactic center, but not eject it completely. Over time, dynamical friction with stars and dark matter would cause the recoiling black hole to sink back toward the center, but this process takes hundreds of millions of years. There is indirect evidence that gravitational recoils have occurred in some galaxies. Astronomers have discovered several candidates for offset black holes, active galactic nuclei that appear to be displaced from the centers of their host galaxies by distances of several hundred to several thousand light-years. One of the best-studied candidates is the galaxy CXOJ 101527, where X-ray observations reveal an active black hole located about 3,000 light-years from the galaxy's optical center. The displacement could be explained by a gravitational recoil following a recent merger. However, proving this scenario is difficult because there are alternative explanations, such as the black hole residing in a satellite galaxy that is in the process of merging with the main galaxy. Distinguishing between these possibilities requires detailed observations of the kinematics and stellar populations in the region around the offset black hole. For Holmburg 15A, there is no evidence of a significant recoil. The black hole appears to be centered on the galaxy, with no measurable offset between the kinematic center and the photometric center. This suggests that either the most recent major merger did not produce a large kick, or enough time has passed since the merger for any recoil displacement to have been damped by dynamical friction. Given the age of the galaxy and the smooth, relaxed appearance of its light distribution, the latter explanation seems more plausible. The black hole has had billions of years to settle back into the center of the gravitational potential well, erasing any memory of earlier recoil events. Nonetheless, the possibility of past recoils affecting the galaxy's evolution cannot be entirely ruled out. If the black hole was temporarily displaced from the galactic center, it would have passed through regions with different stellar densities, potentially scattering stars and altering the orbital structure in ways that might still be detectable with sufficiently sensitive observations. The study of gravitational recoils has important implications for understanding black hole demographics across cosmic time. If large recoil kicks are common, then a significant fraction of massive galaxies might contain wandering black holes that are displaced from the galactic center or even ejected into intergalactic space. These wandering black holes would be difficult to detect unless they are actively accreting and producing observable radiation. Moreover, if black holes can be ejected from galaxies, this places limits on how massive they can grow, because ejected black holes lose access to the gas and stellar material needed for further accretion. The fact that ultramassive black holes like the one in Holmburg 15A exist at all suggests that catastrophic recoil ejections are not the norm. At least for the most massive systems, the configurations of spins required for extreme kicks may be rare in nature, or the mergers that built these black holes may have occurred in orientations that minimize the recoil. When supermassive black holes merge, asymmetric gravitational wave emission can impart a recoil kick to the remnant, potentially displacing it from the galactic center. For non-spinning or unequal mass systems, these kicks are modest, but rapidly spinning black holes can experience recoil velocities of thousands of kilometers per second, in rare cases exceeding galactic escape speeds. Observations of offset active galactic nuclei suggest such recoils occur, though alternative explanations remain. In Holmburg 15A, the black hole is centrally located, indicating any past recoil has long since been damped by dynamical friction or was never extreme. The final parsec problem. One of the great puzzles in the study of supermassive black hole mergers is known as the final parsec problem. When two galaxies merge and their black holes sink toward the center of the remnant galaxy, they initially lose orbital energy through dynamical friction with stars and gas. This process is efficient as long as the black holes are far apart and interacting with a large volume of material. However, as the black holes get closer and their binary shrinks to a separation of roughly 1 parsec, about 3 light-years, the efficiency of dynamical friction drops dramatically. At this stage, the black holes have already scattered or ejected most of the stars on orbits that intersect the binary, creating a loss cone, a range of orbital parameters where stars have been depleted. Without stars to interact with, the binary's orbital decay stalls, and it can take longer than the age of the universe for gravitational wave emission alone to bring the black holes together from a separation of 1 parsec. This is a problem because observations clearly show that supermassive black holes do merge. The existence of galaxies like Holmburg 15A with depleted cores is evidence that binary black holes formed and eventually coalesced. Moreover, recent results from pulsar timing arrays suggest a gravitational wave background consistent with many supermassive black hole mergers occurring throughout the universe. So if binary black holes regularly stall at parsec scale separations, what mechanisms allow them to overcome this barrier and merge? Several solutions to the final parsec problem have been proposed, each involving ways to replenish the loss cone and allow continued interaction between the binary and surrounding matter. One possibility is that triaxial galaxy shapes help. In a triaxial potential, stellar orbits are more complex and can repeatedly pass near the galactic center even after being scattered once. This allows stars to interact with the binary multiple times, continuously extracting energy and causing the binary to shrink. Another potential solution involves gas dynamics. If the galactic nucleus contains a significant reservoir of gas, that gas can form a circumbinary disk, a disk of material orbiting both black holes. The interaction between the binary and the circumbinary disk can drive angular momentum transfer, causing gas to flow inward toward one or both black holes while carrying away orbital energy from the binary. This process can be quite efficient, potentially reducing the merger timescale from billions of years to just tens of millions of years. However, for this mechanism to work, the galaxy must retain enough gas in its central region after the merger, and this may not always be the case. Major galaxy mergers often trigger starbursts that consume much of the available gas, and feedback from the black holes themselves can expel gas from the nucleus. Nonetheless, simulations suggest that even modest amounts of residual gas can significantly accelerate binary evolution. A third possibility involves three-body interactions with a third supermassive black hole. If a galaxy experiences multiple major mergers in relatively quick succession, it might temporarily host three supermassive black holes in its nucleus, and this may not always be the case. Major galaxy mergers often trigger starbursts that consume much of the available gas, and feedback from the black holes themselves can expel gas from the nucleus. Nonetheless, simulations suggest that even modest amounts of residual gas can significantly accelerate binary evolution. A third possibility involves three-body interactions with a third supermassive black hole. If a galaxy experiences multiple major mergers in relatively quick succession, it might temporarily host three supermassive black holes in its nucleus instead of just two. The presence of a third black hole creates a dynamically unstable system where repeated close encounters can efficiently extract energy from the orbits. In some cases, one of the three black holes is ejected from the galaxy, while the remaining two form a tighter binary that can then merge. This scenario is particularly relevant for central cluster galaxies like Holmburg 15A, which experience frequent mergers and might plausibly host multiple black holes simultaneously at certain epochs in their history. Observational evidence for triple black hole systems is limited but growing, with a handful of candidates identified based on spectroscopic or X-ray observations showing complex kinematic signatures. Dark matter may also play a role in solving the final parsec problem, though this possibility is less well explored. If dark matter particles can interact with each other beyond just gravitational interactions, so-called self-interacting dark matter, then dark matter near the galactic nucleus might be able to scatter off the binary black hole and extract energy. This would replenish the loss cone with dark matter particles that continue to interact with the binary even after stars have been depleted. However, current constraints on dark matter properties make this scenario somewhat speculative. Most dark matter models assume that dark matter interacts only gravitationally, and there is no direct evidence for additional interactions. Nevertheless, the final parsec problem remains an active area of research, with astronomers using increasingly sophisticated simulations to explore the range of physical processes that might allow binary black holes to merge within a reasonable timescale. A central challenge in understanding supermassive black hole mergers is the final parsec problem. As two black holes form a binary following a galaxy merger, dynamical friction efficiently shrinks their orbit at large separations. However, once the binary reaches separations of about 1 parsec, nearby stars have largely been ejected, depleting the loss cone and causing orbital decay to stall. Without additional mechanisms, gravitational wave emission alone would take longer than the age of the universe to complete the merger. Yet observations of depleted galaxy cores and gravitational wave backgrounds indicate that such mergers do occur. Proposed solutions include triaxial galaxy shapes that continuously funnel stars toward the center, interactions with circumbinary gas disks that transfer angular momentum efficiently, and three-body interactions involving a third supermassive black hole during successive mergers. These processes can overcome the stall and allow black hole binaries to merge within cosmologically relevant timescales. Radio jets and AGN activity. Although the black hole in Holmburg 15A is currently in a relatively quiescent state, not actively consuming large amounts of matter, it is not entirely dormant. Radio observations using the Very Large Array have detected weak radio emission from the galactic nucleus, along with a pair of small radio jets extending about 7,000 light-years in opposite directions from the center. These jets are streams of relativistic plasma, charged particles accelerated to nearly the speed of light, that are launched from the immediate vicinity of the black hole. The presence of jets indicates that the black hole is accreting at least a small amount of material, and that this accretion is magnetically mediated. The jets are thought to form when magnetic field lines threading the accretion disk or the black hole's ergosphere extract rotational energy from the system and channel it into collimated outflows perpendicular to the disk. The jets in Holmburg 15A are much smaller and weaker than those seen in powerful radio galaxies like Cygnus A or M87, which have jets extending millions of light-years into intergalactic space. This suggests that the accretion rate onto the black hole is currently very low, producing only modest AGN activity. The black hole is likely accreting in a radiatively inefficient mode, where the inflowing material does not form a standard geometrically thin accretion disk. Instead, the gas forms a hot, geometrically thick flow, where most of the gravitational energy is stored as thermal energy in the gas, rather than radiated away. This type of accretion flow, known as an advection-dominated accretion flow, or ADAF, is typical of black holes with very low accretion rates. The jets produced by ADAFs are generally weaker than those from highly accreting systems, but they can still have significant effects on the surrounding medium. Even though Holmburg 15A's jets are relatively small, they are interacting with the hot intracluster medium and inflating the X-ray cavities observed in Chandra images. As the jets plough through the gas, they displace it, creating low-density bubbles that rise buoyantly outward from the galactic center. These bubbles carry energy deposited by the jets into the surrounding medium, heating the gas and preventing it from cooling too rapidly. The power required to inflate the observed cavities can be estimated from their size and the pressure of the surrounding gas. For Holmburg 15A, this mechanical power is estimated to be around 10 to the 43rd ergs per second, equivalent to the energy output of millions of supernovae per year. This is substantial, though modest, compared to the most powerful AGN in other clusters. The relatively low AGN power is consistent with the galaxy's quiescent state and low current accretion rate. The episodic nature of AGN activity means that Holmburg 15A's black hole has likely gone through cycles of high and low accretion over its lifetime. During periods of high accretion, triggered perhaps by the infall of gas-rich galaxies or cooling flows bringing gas to the nucleus, the AGN would have been much more powerful, launching stronger jets and heating the intracluster medium more vigorously. These episodes might last for tens to hundreds of millions of years before the fuel supply is exhausted or expelled by feedback. Then the AGN would dim, entering a quiescent phase like the one observed today. Over billions of years, multiple cycles of activity and quiescence would shape the structure of both the galaxy and the surrounding cluster, regulating star formation and determining the final distribution of gas and stars. Understanding this feedback loop is crucial for explaining why massive galaxies like Holmberg 15A are red and dead rather than blue and star-forming. Observational campaigns to monitor Holmberg 15A at multiple wavelengths, radio, optical, X-ray and infrared, can provide insights into the current state of the black hole's activity and the physical processes operating in the galactic nucleus. Spectroscopic observations reveal weak emission lines from ionized gas, characteristic of a low ionization nuclear emission line region, or LINER. Liners are common in massive elliptical galaxies and are thought to result from photoionization of gas by hot stars or by weak AGN activity. The emission lines in Holmberg 15A are consistent with ionization by the AGN rather than star formation, indicating that the black hole is indeed accreting, albeit at a low level. Future observations with next-generation telescopes, such as the James Webb Space Telescope or the extremely large telescopes currently under construction, may be able to resolve the structure of the nuclear gas in more detail and probe the accretion physics closer to the black hole. Although Holmberg 15A's black hole is currently quiescent, it is not entirely dormant. Weak radio emission and small jets extending about 7,000 light-years indicate low-level accretion, likely occurring through a radiatively inefficient, advection-dominated accretion flow. These jets interact with the surrounding intracluster medium, inflating X-ray cavities and transferring energy that heats the gas, preventing rapid cooling. Holmberg 15A has likely experienced episodic AGN cycles over billions of years, with periods of high accretion launching stronger jets and quiescent phases similar to today. Spectroscopic observations reveal LINER emission lines consistent with weak AGN activity rather than star formation. Multi-wavelength monitoring and future high-resolution observations will provide deeper insights into the black hole's accretion processes and feedback, illuminating how such ultramassive black holes influence galaxy evolution. Holmberg 15A in the context of cosmic evolution. Understanding Holmberg 15. Requires placing it in the broader context of cosmic structure formation. The current cosmological paradigm, known as lambda CDM, describes a universe dominated by dark energy and dark matter, with ordinary matter making up less than 5% of the total energy density. In this framework, structure grows hierarchically. Small fluctuations in the density of dark matter in the early universe grow under gravity to form the first dark matter halos. These halos merge to form progressively larger halos in a cosmic pyramid scheme that continues to the present day. Galaxies form within these dark matter halos, with baryonic matter, ordinary atoms, cooling and condensing at the centers of halos to form stars. Supermassive black holes grow alongside galaxies, fed by accretion and mergers as galaxies themselves collide and coalesce. Holmberg 15. A represents an endpoint of this hierarchical process. It sits at the center of a rich galaxy cluster, the most massive type of gravitationally bound structure in the universe. The cluster formed through the merger of many smaller groups of galaxies over billions of years. And Holmberg 15A grew by consuming galaxies that fell into the cluster center. Its current mass, 2 to 3 trillion solar masses in stars, is the accumulated result of dozens or hundreds of mergers, each adding to the galaxy's bulk. The black hole at its center likewise grew through mergers and accretion, reaching its current ultramassive state through a combination of both processes. The galaxy's smooth appearance and depleted core indicate that the most recent major mergers occurred long enough ago, at least 1 billion years, for the galaxy to relax into equilibrium. Comparing Holmberg 15A to other massive galaxies at different cosmic epochs provides insights into how such systems evolve. High redshift observations with telescopes like Hubble and James Webb show that massive galaxies in the distant universe, observed when the universe was only a few billion years old, are often more compact and irregular than their local counterparts. They show signs of ongoing mergers with disturbed morphologies, tidal tails, and multiple nuclei. This is consistent with the hierarchical growth picture. Massive galaxies are actively being assembled through mergers at high redshift. As time progresses and we look at galaxies closer to the present day, they become progressively smoother and more relaxed, consistent with mergers becoming less frequent and galaxies settling into equilibrium. Holmburg 15A, observed in the present-day universe, represents the mature end state of this process. The galaxy's chemical composition also tells a story of cosmic evolution. The stars in Holmburg 15A are metal-rich and alpha-enhanced, indicating they formed in massive galaxies where star formation was rapid and intense. The high metallicity reflects the fact that these stars formed from gas that had already been enriched by previous generations of stars, consistent with formation in the early universe when galaxy mergers were common and star formation rates were higher. The alpha enhancement indicates that star formation was quenched, shut off quickly, preventing the slow enrichment of iron from type Ia supernovae. This pattern is seen in massive elliptical galaxies throughout the universe and is one of the key pieces of evidence that such galaxies formed their stars in intense bursts billions of years ago, rather than through steady, ongoing star formation, like the Milky Way. Holmburg 15A also provides a laboratory for testing cosmological models. The relationship between black hole mass and galaxy properties, the M-sigma relation, the correlation with bulge mass, and the correlation with core size, are not just empirical facts, but predictions of theoretical models of galaxy and black hole co-evolution. The fact that Holmburg 15A's black hole lies above the mean M-sigma relation is itself informative. It suggests that the most massive systems may follow different evolutionary pathways than lower mass galaxies, perhaps because mergers play a more dominant role in building ultramassive black holes, or because feedback processes operate differently at the highest masses. By measuring the properties of Holmburg 15A and other extreme systems with high precision, astronomers can refine theoretical models and improve our understanding of the physical processes that govern galaxy formation. Holmburg 15A's environment is equally critical to understanding its growth. It resides at the center of Abell 85, a massive galaxy cluster whose gravitational potential well acts as a cosmic funnel. Galaxies falling into the cluster are stripped of their gas through ram pressure and tidal interactions, which both suppress star formation in the infalling galaxies and feed material into the central galaxy. This process, known as galactic cannibalism, allows Holmburg 15A to continuously accrete stars from its neighbours without generating significant new star formation. The intracluster medium, heated to tens of millions of degrees, also regulates cooling and further limits fresh star formation, leaving Holmburg 15A dominated by its accumulated stellar population. Another intriguing aspect of Holmburg 15A is its unusually large core, a defining feature of core elliptical galaxies. The central region is depleted of stars relative to what a simple extrapolation of its outer light profile would predict. This core is thought to result from the gravitational interactions of supermassive black holes during galaxy mergers. When two massive black holes spiral together, they eject stars from the nucleus through three-body interactions, scouring out the core. Holmburg 15A's exceptionally large core therefore serves as a record of its violent merger history, providing a direct link between black hole growth and the structural evolution of the galaxy. Finally, Holmburg 15A challenges astronomers to push the limits of observational techniques, measuring the mass of its central black hole, thought to be among the largest known, requires precise stellar kinematics and careful modelling of the galaxy's gravitational potential. High-resolution spectroscopy and adaptive optics allow astronomers to track the motions of stars near the core, while X-ray observations reveal the hot gas dynamics within the cluster. Each measurement refines not only the understanding of Holmberg 15A itself, but also informs the broader field of galaxy evolution, helping to constrain how the most massive galaxies in the universe assemble, grow, and interact with their environments over cosmic time. The nature of elliptical galaxies. Holmberg 15 belongs to the class of elliptical galaxies, which differ fundamentally from spiral galaxies like the Milky Way. While spirals are characterized by rotating disks, spiral arms, and ongoing star formation, ellipticals are spheroidal or ellipsoidal systems supported by the random motions of their stars, with little rotation and negligible star formation. The formation of elliptical galaxies is thought to occur primarily through galaxy mergers. When two spiral galaxies collide, their ordered disk structures are disrupted by gravitational interactions. Stars are scattered onto random orbits, and the angular momentum of the disks is lost through dynamical friction and tidal torques. The result is a pressure-supported elliptical galaxy whose stars move on complex three-dimensional orbits. Subsequent dry mergers with little gas involved between ellipticals can produce ever larger ellipticals without dramatically altering this fundamental structure. The properties of elliptical galaxies follow several empirical scaling relations. The Faber-Jackson relation correlates the luminosity of an elliptical galaxy with its central velocity dispersion. More luminous ellipticals have higher velocity dispersions, reflecting their deeper gravitational potential wells. The fundamental plane is a tighter three-parameter relation involving the effective radius, surface brightness, and velocity dispersion, which describes the distribution of elliptical galaxies in a two-dimensional plane within this three-dimensional parameter space. These relations reflect the fact that elliptical galaxies form a relatively homogeneous family of objects with predictable properties, suggesting they are shaped by similar physical processes despite their wide range in mass. Holmberg 15A, as an extreme example of a supergiant elliptical, lies at one end of these scaling relations, testing whether they continue to hold at the highest masses or whether new physics becomes important. The internal structure of elliptical galaxies reveals further insights into their formation. Most ellipticals show a smooth, featureless light distribution that can be well described by mathematical profiles like the Cetus profile, which characterizes how the surface brightness decreases with radius. However, detailed photometry often reveals subtle deviations from perfect smoothness. Shells, ripples, boxy or disky isophotes, and variations in ellipticity with radius. These features are the fossil remnants of past mergers, slowly fading as stellar orbits phase mix over billions of years. In Holmberg 15A, such features are difficult to detect due to the galaxy's great distance, but careful analysis of deep images has revealed hints of faint tidal structures that could be the remnants of recent minor mergers. The accretion of satellite galaxies that added to Holmberg 15A's mass, but were not large enough to significantly disturb its structure. Elliptical galaxies are often found in dense environments like galaxy clusters, whereas spiral galaxies are more common in the field, regions of lower galaxy density. This environmental dependence reflects the importance of mergers in producing ellipticals. In dense environments, galaxies interact frequently, and mergers are common, preferentially producing ellipticals. In the field, galaxies are more isolated, and major mergers are rare, allowing spirals to persist. Holmberg 15A's location at the center of Abell 85 is thus no accident. It is precisely in such environments that the most massive ellipticals form and grow. The cluster environment also affects the galaxy through ram pressure stripping and tidal interactions, which can remove gas and inhibit star formation, reinforcing the quiescent, red nature of central cluster galaxies. The study of elliptical galaxies like Holmburg 15A is important for understanding the diversity of galaxy types in the universe and the physical processes that produce this diversity. Not all galaxies are the same, and understanding why some are spirals, some are ellipticals, and some are irregular requires understanding the roles of mergers, star formation, gas accretion, and feedback from black holes and supernovae. Holmburg 15A, as one of the most extreme ellipticals known, provides a key test case for theories of galaxy formation and evolution. Its properties, its enormous mass, its depleted core, its quiescent star formation, its ultramassive black hole, are all predictions of models that attempt to explain how the largest galaxies in the universe form and evolve over cosmic time. Holmburg 15. MUSE also provides insights into the role of dark matter in shaping elliptical galaxies. Ellipticals are embedded in massive dark matter halos which dominate the gravitational potential at large radii. Observations of stellar motions, gravitational lensing, and X-ray emission from hot gas allow astronomers to infer the distribution of dark matter within and around these galaxies. In Holmburg 15A, the dark matter halo is likely extremely massive, reflecting the combined contribution of the galaxy itself and the surrounding cluster. The interplay between dark matter and baryons influences the galaxy's structure, the orbital distribution of its stars, and the retention of gas, helping to explain why the galaxy is both so massive and so quiescent. Another intriguing aspect of Holmburg 15A is the connection between its stellar population and the chemical enrichment history of the universe. Detailed spectroscopic studies reveal that its stars are not only old, but also enriched in alpha elements like oxygen, magnesium, and silicon relative to iron. This pattern indicates that the bulk of the stars formed rapidly in the early universe, dominated by Type II supernovae from massive stars. The lack of significant iron enrichment from Type Ia supernovae suggests that star formation was truncated early, likely due to feedback from the central black hole or the cluster environment, which expelled or heated the remaining gas. Holmburg 15A thus preserves a fossil record of early, intense star formation in massive galaxies. Holmburg 15A serves as a laboratory for extreme astrophysics and testing theoretical models. Its ultramassive black hole, one of the largest known, challenges existing scaling relations such as the M-sigma and M-bulge correlations, raising questions about whether such relations are universal or break down at the highest masses. Studying Holmburg 15A's stellar dynamics, core structure, and halo properties allows astronomers to refine models of galaxy assembly, merger-driven growth, and black hole co-evolution. Moreover, its position at the center of a massive cluster makes it a key system for understanding the co-evolution of galaxies and large-scale structure. By pushing the limits of both observations and theory, Holmburg 15A illuminates the processes that produce the universe's largest and most enigmatic galaxies. The galaxy's stellar halo and outer regions. Beyond the bright central regions of Holmburg 15A lies an extensive stellar halo, a diffuse envelope of stars that extends to hundreds of thousands of light years from the galactic center. This halo contains stars that were stripped from satellite galaxies during mergers or ejected from the main galaxy by gravitational interactions. The stellar halo is extremely faint. Its surface brightness is thousands of times lower than the bright core, making it difficult to observe and study. However, it contains important clues about the galaxy's merger history. The stars in the halo are expected to be old and metal-poor, reflecting their origin in smaller galaxies that were accreted by Holmburg 15A. By measuring the distribution, velocities, and chemical compositions of halo stars, astronomers can reconstruct which satellite galaxies were accreted and when. Observations of Holmburg 15A's outer regions reveal that the galaxy's light profile continues outward to at least 300,000 light-years from the center, possibly farther. The exact extent is difficult to determine because the surface brightness drops below detection limits of current instruments. However, comparison with simulations suggests that the dark matter halo extends much farther still, reaching several million light-years. The transition from the stellar halo to the intracluster light, stars that are no longer gravitationally bound to any individual galaxy, but instead orbit in the gravitational potential of the entire cluster, is gradual and not sharply defined. Some of the stars in the outskirts of Holmburg 15A may be on orbits that take them far from the galaxy, while others may have been stripped so completely from their parent galaxies that they no longer belong to any galaxy at all. The velocity structure of the stellar halo provides additional information about the galaxy's assembly history. If the halo formed from many small accretion events, the destruction of numerous dwarf galaxies, its velocity distribution should be relatively smooth and well mixed, with no strong signatures of individual merger events. On the other hand, if the halo was built by a few major mergers, there should be kinematic substructure, groups of stars with coherent velocities corresponding to the remnants of disrupted galaxies. Spectroscopic surveys that measure stellar velocities in the halo can test these predictions, but obtaining such observations for a galaxy as distant as Holmburg 15A is extremely challenging with current technology. Future instruments, particularly the extremely large telescopes, will make such studies feasible. The outer regions of Holmburg 15A are also the site of interactions with the intracluster medium. As the galaxy moves through the hot gas filling the Abell 85 cluster, though as the central galaxy, its motion is relatively slow, ram pressure from the gas can strip loosely bound material from the galaxy's outskirts. This process primarily affects gas rather than stars, but over long timescales it can influence the galaxy's structure. Additionally, tidal interactions with other galaxies in the cluster can perturb the outer halo, creating tidal tails or streams. These features are expected to be very faint and extended, requiring deep wide-field imaging to detect. Surveys designed to study the low surface brightness outskirts of galaxies, such as the Dragonfly telephoto array, have begun to reveal the outer structures of nearby galaxies, and similar techniques applied to Holmburg 15A could provide new insights. The stellar halo of Holmburg 15A also provides a unique opportunity to study the chemical evolution of accreted material. While the halo stars are generally old and metal-poor compared to the central regions, detailed spectroscopy can reveal variations in elemental abundances that trace the histories of the dwarf galaxies from which they originated. For example, differences in alpha element enhancement or ion content can indicate whether the stars formed rapidly in small galaxies or over longer periods. These chemical fingerprints allow astronomers to reconstruct the assembly timeline of Holmburg 15A, identifying which mergers occurred early in cosmic history and which are more recent, providing a fossil record of galaxy growth. Beyond the stars themselves, the outer halo interacts dynamically with the surrounding dark matter. Stars at these extreme distances are sensitive traces of the galaxy's gravitational potential, which is dominated by dark matter in the outskirts. By mapping the velocities of halo stars, astronomers can constrain the shape and extent of the dark matter halo, testing cosmological predictions about how massive galaxies and clusters assemble. Holmburg 15A, with its enormous mass and extensive halo, represents one of the few systems where these measurements are feasible, offering a rare laboratory for studying the interplay between baryonic matter and dark matter on scales of hundreds of thousands to millions of light years. The halo and intracluster regions of Holmburg 15A also hold clues about the fate of stars in dense cluster environments. As stars are stripped from satellite galaxies or scattered from the main galaxy, they can become part of the intracluster light, a diffuse population orbiting the cluster as a whole. Studying the density, distribution, and kinematics of these stars informs models of cluster evolution, including how material is exchanged between galaxies and the intracluster medium. Observing these processes in Holmburg 15A can provide insights not only into this galaxy's history, but also into the broader picture of galaxy cluster evolution, showing how even the largest and most massive galaxies continue to interact with their environment over cosmic time. Cosmic ripples, black holes, and beyond. The discovery and study of Holmburg 15A's ultramassive black hole have implications that extend far beyond a single galaxy. By pushing the boundaries of black hole mass measurements and exploring the most extreme systems, astronomers gain insights into the fundamental physical processes that govern black hole and galaxy evolution throughout the universe. One key question is whether there is an upper limit to black hole mass. Theoretical arguments suggest that black holes cannot grow arbitrarily large because radiation pressure from accreting material and feedback from jets and winds eventually becomes strong enough to halt further growth. The existence of black holes in the 20 to 40 billion solar mass range suggests that this upper limit, if it exists, is at least this high. Finding black holes more massive than Holmburg 15A's, or failing to find them despite extensive searches, would provide important constraints on the physics of black hole growth. The study of ultramassive black holes also connects to broader questions about the role of black holes in regulating galaxy evolution. The correlation between black hole mass and galaxy properties suggests that black holes and galaxies co-evolve through a feedback loop where the black hole's growth is tied to the growth of the galaxy, and the black hole's feedback regulates star formation and gas content in the galaxy. This co-evolution is thought to explain the red and dead nature of massive elliptical galaxies. Once the central black hole reaches a critical mass, its feedback becomes strong enough to expel or heat all the gas in the galaxy, shutting off star formation. Holmburg 15A, with its quiescent star formation and powerful but moderate AGN activity, is a key example of this process in action. Understanding how feedback operates in this galaxy helps refine models that are applied to galaxies throughout the universe. Holmburg 15A also serves as a target for multi-messenger astronomy, the study of astronomical objects using multiple forms of radiation and signals. While the galaxy is currently too far away and too quiescent to be a strong gravitational wave source, future mergers could change that. If Holmburg 15A merges with another massive galaxy in the next few billion years, the resulting black hole binary would emit gravitational waves detectable by future space-based observatories. Simultaneously, the merger would produce electromagnetic signatures, increased AGN activity as gas is funneled toward the black holes, possible tidal disruption events as stars are torn apart by the black hole's gravity, and changes in the X-ray emission from the intracluster medium as jets and winds interact with the hot gas. Coordinated observations across the electromagnetic spectrum and gravitational wave detectors would provide a comprehensive picture of the merger process. The techniques developed to study Holmburg 15A, integral field spectroscopy, triaxial orbit modelling, deep imaging, and X-ray observations, are applicable to many other galaxies. As technology improves and more galaxies are surveyed with these techniques, the sample of well-studied ultramassive black holes will grow. This will enable statistical studies that address questions like: how common are ultramassive black holes? What fraction of massive galaxies host them? How does the black hole mass function evolve over cosmic time? Are there systematic differences between black holes in clusters versus those in the field? Answering these questions requires not just detailed studies of individual objects like Holmburg 15A, but large surveys that provide representative samples of galaxies across a range of masses, environments, and cosmic epochs. The study of Holmburg 15A also informs our understanding of the growth history of cosmic structures. Ultramassive black holes like the one at its center are intimately tied to the hierarchical assembly of galaxies and clusters. By examining the galaxy's stellar population, core structure, and halo dynamics, astronomers can reconstruct the sequence of mergers and accretion events that led to its current mass. This helps refine models of galaxy cluster evolution and the role of central galaxies in shaping their environment. Holmburg 15A, as a central cluster galaxy with an extremely massive black hole, represents an endpoint of these processes, providing a natural laboratory to test theories of galaxy formation on the larger scales. Moreover, Holmburg 15A challenges existing theoretical models of black hole feedback and accretion physics. The energy output of such a massive black hole, through jets, winds, and radiation, has profound effects on the surrounding interstellar and intracluster medium. Understanding how this energy is deposited, how efficiently it couples with the gas, and how it suppresses star formation informs cosmological simulations that aim to reproduce the observed distribution of galaxy types and luminosities in the universe. Observations of Holmburg 15A's AGN, combined with measurements of the surrounding hot gas, provide crucial benchmarks for these models, particularly in the high-mass regime where feedback processes may behave differently from those in lower-mass galaxies. Holmburg 15. A highlights the potential for future discoveries in extreme astrophysics. Next-generation telescopes, both ground and space-based, will allow astronomers to probe even fainter stellar halos, detect more subtle tidal features, and measure the kinematics of stars at unprecedented distances. Space-based gravitational wave observatories like LISA will eventually detect mergers of ultramassive black holes, while multi-wavelength observatories will trace the electromagnetic signatures of these events. Holmburg 15. I serves as a cornerstone for planning such observations, bridging the gap between theory and observation. By studying galaxies at the extremes of mass, luminosity, and black hole size, astronomers gain crucial insights into the universe's most powerful engines and the physical laws that govern their growth and influence. Decoding an ultramassive enigma. Measuring the mass of a black hole as massive and as distant as the one in Holmburg 15A is fraught with challenges and systematic uncertainties. The primary difficulty is obtaining high-quality spectra of the faint central region of the galaxy. Despite being one of the brightest galaxies in its cluster, Holmburg 15A's core is exceptionally faint due to the stellar depletion caused by core scouring. This means that even with large telescopes like the Very Large Telescope, or Keck, long exposure times are required to accumulate enough photons to measure stellar velocities with the precision needed for dynamical modelling. The observations must be conducted under excellent atmospheric conditions to minimize the blurring effects of turbulence, and sophisticated data reduction techniques are needed to extract the maximum information from the data. Another source of uncertainty is the modelling itself. Determining a black hole's mass from stellar kinematics requires making assumptions about the galaxy's structure, its shape, the distribution of dark matter, the orbital structure of stars, and the mass-to-light ratio of the stellar population. Different assumptions lead to different derived black hole masses, and there is no unique solution. The 2019 study using MUSE data assumed the galaxy was axisymmetric, while the 2025 study using KCWI data explicitly modelled the galaxy as triaxial. The fact that the triaxial model produced a lower black hole mass, 22 billion versus 40 billion solar masses, demonstrates the importance of these assumptions. Neither measurement is necessarily wrong, but they are answering slightly different questions. What is the black hole mass assuming axisymmetry versus what is the black hole mass allowing for triaxiality? Systematic uncertainties also arise from the stellar population models used to convert observed light into stellar mass. Different stellar population synthesis models make different assumptions about the initial mass function, the distribution of stellar masses at birth, and the evolution of stars over time. These differences can lead to systematic variations in the derived mass-to-light ratio, which propagates into uncertainties in the total stellar mass and, indirectly, the black hole mass. For Holmburg 15A, the old stellar population and well-understood spectral features make this uncertainty smaller than for galaxies with more complex star formation histories, but it is not negligible. Future improvements in stellar population models, informed by detailed studies of stars in the Milky Way and nearby galaxies, will help reduce this uncertainty. The presence of dark matter adds another layer of complexity. While dark matter is subdominant in the central regions where the black hole's gravity is strongest, it becomes increasingly important at larger radii. The exact distribution of dark matter, whether it follows a simple profile like Navarro-Frank white or has more complex structure, affects the gravitational potential and thus the stellar kinematics. Degeneracies between the black hole mass, the stellar mass distribution and the dark matter distribution mean that fitting models to the data cannot uniquely determine all parameters simultaneously. Astronomers address this by using prior information from simulations and other observations, but residual uncertainties remain. The quoted error bars on black hole mass measurements reflect both statistical uncertainties from the data quality and systematic uncertainties from modelling choices, with the latter often dominating for massive distant systems like Holmburg 15A. Despite these challenges, the measurement of Holmburg 15A's black hole mass represents a remarkable achievement. A decade ago, measuring black hole masses in galaxies at distances of nearly 800 million light-years was essentially impossible. Advances in instrumentation, particularly the development of integral field spectrographs like MUSE and KCWI, and improvements in computational modelling have made such measurements routine, at least for the brightest galaxies in rich clusters. The fact that two independent measurements using different instruments and different modelling techniques converge on similar mass estimates, even if they differ by a factor of 2, provides confidence that the black hole is indeed ultramassive, with a mass somewhere in the 20 to 40 billion solar mass range. Future observations with even more powerful instruments will continue to refine this estimate and reduce the uncertainties. Another observational challenge comes from the spatial resolution required to resolve the black hole's sphere of influence. For Holmburg 15A, even with the largest ground-based telescopes, the angular size of the region where the black hole dominates the gravitational potential is extremely small, on the order of a few hundredths of an arcsecond. Adaptive optic systems can partially correct for atmospheric blurring, but the faintness of the core and the need for long exposures limit the achievable signal-to-noise ratio. Space-based instruments, such as those on the Hubble Space Telescope, avoid atmospheric effects but lack the spectroscopic capabilities of large, ground-based telescopes. Future extremely large telescopes with mirror diameters exceeding 30 meters and next-generation adaptive optics will allow astronomers to probe these innermost regions with unprecedented detail, potentially reducing uncertainties in black hole mass measurements. Time variability and dynamical relaxation add further complications. The central regions of Holmburg 15A may host stars on highly eccentric orbits influenced by past mergers or interactions with the black hole. While the galaxy as a whole is in approximate equilibrium, small-scale deviations from steady-state motion can bias mass estimates if not properly accounted for. Similarly, the presence of unresolved stellar populations, such as binary stars or stellar remnants like neutron stars and black holes, can subtly alter the observed velocity dispersion. These effects are difficult to quantify, but can contribute to systematic uncertainties, highlighting the importance of sophisticated dynamical models that include triaxiality, anisotropic orbital distributions, and realistic stellar populations. The combination of multiple observational datasets introduces its own challenges. Different instruments operate at different wavelengths, spectral resolutions, and fields of view, each with unique calibration requirements and noise characteristics. Integrating these datasets into a coherent model requires careful cross-calibration and error propagation. Despite these hurdles, the convergence of results from multiple studies using independent instruments, such as MUSE, KCWI, and Hubble imaging, demonstrates the robustness of the overall conclusions. Continued improvements in instrumentation, modelling, and computational power promise to refine black hole mass estimates further, allowing astronomers to explore the upper limits of black hole growth and better understand the co-evolution of ultramassive black holes and their host galaxies. The comparison with M87 and other famous black holes. Holmburg 15A's black hole inevitably invites comparison with other famous supermassive black holes, particularly M87, the galaxy that hosts the first black hole ever directly imaged. M87 is a giant elliptical galaxy at the center of the Virgo cluster, located about 55 million light-years from Earth, much closer than Holmburg 15A. M87's black hole has a mass of approximately 6.5 billion solar masses, making it significantly less massive than Holmburg 15A's, though still enormous by any standard. The key advantage of M87 is its relative proximity, which allowed the Event Horizon telescope to resolve the black hole's event horizon and produce the iconic image released in 2019. That image showed a bright ring of emission surrounding a dark shadow, with the shadow corresponding to the photon sphere, the region where light orbits the black hole before either escaping or falling in. The physics governing the two black holes is fundamentally the same, described by Einstein's general relativity, but their observational appearances differ due to their different masses, distances, and accretion rates. M87's black hole is currently more active than Holmburg 15A's, accreting at a higher rate and producing a powerful jet visible across the electromagnetic spectrum from radio to X-rays and even gamma rays. This jet extends for thousands of light years and has been studied extensively with radio telescopes and space-based observatories. The jet's origin near the black hole's event horizon makes M87 an ideal laboratory for studying the physics of jet formation and the interaction between black holes and magnetic fields. Holmburg 15A's jets are much weaker and smaller, indicating lower accretion rates and less energetic AGN activity. But they still provide valuable information about feedback processes in the cluster environment. Another important comparison is with Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Sagittarius A star has a mass of only about 4 million solar masses, roughly 5,000 times less massive than Holmburg 15A's black hole. But it has the enormous advantage of proximity. Located just 26,000 light-years away, Sagittarius A star's immediate environment can be studied in exquisite detail. Individual stars orbiting the black hole have been tracked for decades, providing precise measurements of the black hole's mass and testing general relativity in the strong field regime. The Event Horizon Telescope has also imaged Sagittarius A star's shadow, though the image is more challenging to produce than M87's, because the accretion flow around Sagittarius A star varies on timescales of minutes, requiring sophisticated image reconstruction techniques. Comparing these three black holes, Holmburg 15A, M87, and Sagittarius A star, highlights the diversity of supermassive black holes and the range of physical scales involved. The black holes span more than 4 orders of magnitude in mass, from 4 million to 40 billion solar masses. Their host galaxies range from the Milky Way, a spiral galaxy with ongoing star formation, to M87 and Holmburg 15A, giant ellipticals that are red and dead. Their distances range from 26,000 light-years to 787 million light-years. Their accretion rates and AGN activity levels vary from quiescent to highly active. Yet all three are governed by the same physical laws, and studying them collectively provides a comprehensive picture of black hole physics across the full range of masses and environments found in the universe. One particularly intriguing aspect of these comparisons is the relationship between black hole mass and the Schwarzschild radius, which scales linearly with mass. For Sagittarius A star, the Schwarzschild radius is about 12 million kilometers, roughly 1/10 the radius of Earth's orbit around the Sun. For M87, it is about 19 billion kilometers, comparable to the size of our solar system out to Neptune's orbit. For Holmburg 15A, as we have noted, it is about 65 billion kilometers, roughly 3 times larger still. These enormous sizes mean that the event horizons of ultramassive black holes are comparable to the distances between stars in dense stellar systems. If a star were to wander within a few Schwarzschild radii of Holmburg 15A's black hole, it would be tidally disrupted, torn apart by tidal forces into a stream of gas that would accrete onto the black hole. Such tidal disruption events are rare but observable, producing bright flares of radiation that can be detected across vast distances. Holmburg 15A's black hole also emphasizes the limits of current observational capabilities. Unlike M87 and Sagittarius A star, which are close enough for detailed imaging of their event horizons or stellar orbits, Holmburg 15A lies nearly 800 million light-years away. At this distance, even the most powerful telescopes cannot resolve the immediate vicinity of the black hole. Instead, astronomers must rely on indirect methods, such as measuring the motions of stars in the galaxy's central region, to infer the black hole's mass. This demonstrates how the study of ultramassive black holes at cosmological distances requires both precision instrumentation and sophisticated modelling, combining observations across multiple wavelengths to build a coherent picture of these extreme systems. The comparison also highlights differences in black hole growth and feeding mechanisms. M87 and Holmburg 15A are both central galaxies in clusters, but the history of gas inflows and mergers differs. M87's relatively active jet suggests ongoing accretion of gas, likely from the surrounding intracluster medium or minor mergers. Holmburg 15A, by contrast, shows weaker AGN activity, implying lower accretion rates despite its larger mass. These differences provide insights into how environment and merger history regulate black hole growth. Studying such contrasts helps refine models of black hole feedback, which influence star formation, gas heating, and the evolution of galaxies in dense cluster environments. Comparing Holmburg 15A, M87, and Sagittarius A star illustrates the extreme range of timescales and physical processes involved. In the Milky Way, stars orbit Sagittarius A star in years or decades, allowing real-time tests of gravity. Around M87, orbital timescales extend to hundreds or thousands of years, while in Holmburg 15A, stars near the black hole may take millions of years to complete an orbit. Similarly, the formation of jets, tidal disruption events, and accretion dynamics occur on vastly different scales. Yet by studying all three systems together, astronomers can test whether the physical principles derived from nearby small black holes apply equally to the universe's most massive ones. Holmberg 15A, therefore, provides a crucial bridge connecting local black hole physics with the extreme, ultramassive regime found in the centers of galaxy clusters. The long-term life of an ultramassive galaxy. Looking billions of years into the future, what will become of Holmberg 15A? The galaxy has already undergone a long and violent history of mergers and growth, but its evolution is far from over. The Abell 85 cluster continues to accrete galaxies from its surroundings as smaller groups fall into the cluster's gravitational potential well. Some of these infalling galaxies will eventually merge with Holmberg 15A, adding to its stellar mass and feeding its central black hole. Each merger will bring with it a new supermassive black hole, which will sink to the center through dynamical friction and eventually merge with Holmberg 15A's black hole, increasing its mass further. Over the next several billion years, the black hole could grow by tens of percent or even double in mass, depending on how many massive galaxies fall into the cluster and merge with the central galaxy. However, the rate of mergers is expected to decrease over time. In the early universe, when galaxies were more closely packed and the universe was smaller, mergers were common and frequent. As the universe expands and galaxies become more spread out, the merger rate declines. Abell 85 is a mature cluster that has already accreted most of its mass, and future growth will be slower than in the past. The next major merger might not occur for several billion years, and each subsequent merger will be separated by progressively longer time intervals. Eventually, the cluster will exhaust its supply of nearby galaxies to accrete, and growth will essentially cease. Holmberg 15A will then evolve passively, with its stellar population aging and fading, but no significant new stars being formed. The black hole's future evolution is similarly sedate. In the absence of significant gas accretion or major mergers, the black hole will remain quiescent, growing only through the occasional accretion of stars or small amounts of gas. The rate of tidal disruption events will remain low, and the AGN activity will continue to be weak. The black hole will settle into a stable configuration at the center of the galaxy, its gravitational influence extending outward, but largely static. Over timescales of many billions of years, longer than the current age of the universe, stellar evolution will change the character of the galaxy. The most massive stars still present today will exhaust their nuclear fuel and die, leaving behind white dwarfs, neutron stars, or black holes. The galaxy's light will be increasingly dominated by low-mass red dwarfs and white dwarfs, causing the overall luminosity to decline slowly over time. On even longer timescales, far into the distant future, the accelerating expansion of the universe due to dark energy will cause galaxy clusters to become isolated islands in an ever-expanding cosmos. Clusters that are currently part of the same supercluster will recede from each other faster than light, disappearing beyond each other's cosmic horizons. Abell 85 will become disconnected from the broader cosmic web, isolated within a region of space that can no longer receive light or information from the rest of the universe. Within the cluster, however, gravity will continue to dominate, and the cluster's evolution will proceed based solely on its internal dynamics. Galaxies within the cluster will continue to merge, though at a decreasing rate. Holmberg 15A will likely remain the central galaxy, growing slowly as it consumes whatever smaller galaxies remain. In the extremely distant future, tens to hundreds of trillions of years from now, the universe will enter an era dominated by the remnants of dead stars. Most stars will have exhausted their nuclear fuel and evolved into white dwarfs, neutron stars, or black holes. The galaxy will be a dark, cold place, illuminated only by the feeble glow of the lowest mass stars still burning their hydrogen fuel and the occasional flash from collisions between stellar remnants. The supermassive black hole will persist, growing imperceptibly through the accretion of these remnants and through the rare mergers with other black holes. Eventually, on timescales of 10 to the 100 years or more, numbers so large they are beyond human comprehension, even the black hole will evaporate through Hawking radiation, leaving behind only a faint spray of elementary particles dispersing into an ever-expanding, ever-colder universe. Even before reaching the ultimate fate of the universe, Holmberg 15A will experience subtle, internal evolution. Over the next several billion years, the galaxy's stellar orbits will continue to phase mix, smoothing out any residual tidal features or asymmetries left over from past mergers. Dynamical interactions among stars and stellar remnants, including black holes and neutron stars, will slowly redistribute mass throughout the galaxy, a process known as violent relaxation. Though invisible to casual observation, this ongoing internal evolution will further homogenize the galaxy, making it an even more textbook example of a relaxed, massive elliptical galaxy. The intracluster environment will continue to play a role as well. While major mergers will become increasingly rare, small satellite galaxies, globular clusters, and even interstellar gas clouds may still interact with Holmberg 15A. These minor interactions can perturb the outer stellar halo, adding faint streams or shells that persist for billions of years. In addition, stars that wander too close to the central black hole may be tidally disrupted, producing occasional flares that briefly illuminate the surrounding galaxy. These events will become rarer over time, but they will serve as intermittent reminders that even the largest, most massive galaxies remain dynamic systems on cosmic timescales. Holmberg 15A's long-term evolution exemplifies the ultimate fate of structure in a dark energy-dominated universe. As expansion isolates galaxy clusters from one another, Holmberg 15A and its cluster companions will become part of a gravitationally bound island in a vast, dark void. Stellar evolution, black hole mergers, and the gradual decay of stellar remnants will define the internal life of the galaxy over trillions of years. Even as the universe fades to near absolute zero, Holmberg 15A will endure as a massive, slowly dimming monument to the hierarchical assembly of matter, a lasting witness to cosmic history long after the era of luminous stars has ended. Holmberg 15A, a catalyst for discovery. The study of Holmberg 15A and its ultramassive black hole represents a milestone in our exploration of the universe. It demonstrates the power of modern astronomical techniques to probe the most extreme objects in the cosmos, measuring properties that would have seemed impossible to determine just a few decades ago. The discovery of the ultramassive black hole at the galaxy's core has reshaped our understanding of black hole formation and growth, showing that black holes can reach masses far exceeding those of typical supermassive black holes in galaxies like the Milky Way. It has provided crucial tests of theories of galaxy mergers, core scouring, and AGN feedback, confirming predictions and revealing new complexities that were not anticipated. Yet for every question answered, new questions emerge. What is the exact mass of the black hole, and can we reduce the uncertainty between the 22 billion and 40 billion solar mass estimates? What is the black hole's spin, and what does it reveal about the merger history that built it? Are there even more massive black holes waiting to be discovered in other supergiant elliptical galaxies? Or does Holmberg 15A represent the extreme upper end of the black hole mass distribution? How common are galaxies like Holmberg 15A, and what fraction of galaxy clusters host such extreme central galaxies? What role did the black hole play in shaping not just its host galaxy, but the entire cluster environment? These questions drive ongoing research and motivate new observations with increasingly powerful telescopes. The techniques and insights gained from studying Holmburg 15A will be applied to a growing sample of massive galaxies in the coming years. As surveys expand and more galaxies are observed with integral field spectrographs, the census of ultramassive black holes will grow, allowing for statistical studies that complement the detailed individual case studies. These surveys will reveal whether Holmburg 15A is typical or an outlier, whether there are environmental factors that favour the formation of ultramassive black holes, and whether the scaling relations between black hole mass and galaxy properties extend all the way to the most extreme systems. Each new measurement adds a data point to the empirical relations that guide theoretical models, helping to refine our understanding of the physical processes at work. Future facilities will revolutionise our ability to study systems like Holmburg 15A. The extremely large telescopes will provide unprecedented spatial resolution and sensitivity, allowing us to resolve smaller structures and detect fainter features. Space-based observatories will observe at wavelengths inaccessible from the ground, revealing components of the system that are hidden by Earth's atmosphere. Gravitational wave detectors will open an entirely new window on black hole mergers, providing direct observations of events that can currently only be inferred from indirect evidence. Multi-messenger astronomy, combining electromagnetic observations with gravitational wave detections and possibly even neutrino observations, will provide a comprehensive view of the most energetic phenomena in the universe. Holmburg 15A will remain a key target for these facilities, a benchmark system against which models and theories can be tested. The study of Holmburg 15A also connects to the deepest questions in physics: the nature of gravity, the behaviour of matter under extreme conditions, and the ultimate fate of the universe. Black holes are laboratories for testing general relativity in regimes where space-time curvature is extreme, and quantum effects might become important. The observation of gravitational waves from black hole mergers has already confirmed predictions of general relativity with exquisite precision, and future observations will probe even more extreme systems. The interaction between black holes and their environments, through accretion, jets, and feedback, involves a complex interplay of gravity, magnetohydrodynamics, and radiation physics that is not fully understood. Progress in understanding these processes requires both better observations and more sophisticated theoretical models, often informed by large-scale numerical simulations run on the most powerful supercomputers. Holmburg 15A's discovery also underscores the importance of synergy between observational and theoretical astrophysics. Detailed studies of its black hole and host galaxy inform simulations of galaxy formation and evolution, while the predictions of those models guide observational strategies. For example, understanding how mergers and feedback shape central galaxies allows astronomers to target likely hosts of ultramassive black holes in other clusters. Conversely, precise measurements of stellar kinematics, halo structure, and core properties in Holmburg 15A provide critical benchmarks for validating or revising these models. This iterative feedback between theory and observation accelerates progress and ensures that each new discovery has broader implications for the field of extragalactic astronomy. Another important legacy lies in the technological advancements spurred by the quest to study extreme systems like Holmburg 15A. Instruments such as integral field spectrographs, adaptive optics systems, and high-resolution X-ray and radio observatories have been pushed to their limits to extract meaningful data from faint, distant galaxies. The development of sophisticated data reduction pipelines and dynamical modelling techniques has also benefited the study of less extreme systems, improving our ability to measure black hole masses and galaxy properties across a wide range of environments. Holmberg 15A thus represents both a scientific target and a driver of innovation, demonstrating how extreme astrophysical objects push the boundaries of what is observationally possible. Tracing the universe through Holmberg 15A. Holmberg 15. A's story will continue to evolve as new observations add detail and new discoveries place it in broader context. The galaxy that Erich Holmberg catalogued in the 1930s, not knowing its true nature, has become one of the most thoroughly studied objects in extragalactic astronomy. Its ultramassive black hole, once hidden and unknown, is now a landmark in the landscape of cosmic extremes. As astronomy advances into the future, Holmberg 15A will remain a touchstone, a reminder of how far we have come in understanding the universe and how much remains to be discovered. The universe is vast beyond human comprehension, filled with structures and phenomena that challenge our understanding of physics and our sense of place in the cosmos. Holmberg 15. A stands as one of the most extreme examples of what the universe can produce. A galaxy containing trillions of stars, built through countless cosmic collisions over billions of years, harboring a black hole so massive it defies easy explanation. The story of this galaxy is the story of structure formation in the universe, of hierarchical growth through mergers, of the interplay between gravity and feedback, and of the co-evolution of black holes and galaxies. It is a story written in the motions of stars, in the glow of hot gas, and in the gravitational waves that ripple through spacetime when black holes collide. Understanding Holmberg 15. A required pushing observational techniques to their limits, developing new modelling methods, and interpreting data in light of our best theories of cosmology and astrophysics. The measurements of its black hole mass represent the culmination of decades of work building the instruments, refining the techniques, and training the scientists needed to carry out such challenging observations. Each new measurement refines our understanding, reducing uncertainties and revealing new complexities. The revised mass estimate from 40 billion to 22 billion solar masses does not diminish the significance of the discovery. It enhances it, showing that science is self-correcting and that improved methods lead to more accurate results. As we look to the future, Holmberg 15A will continue to be a focal point for studies of ultramassive black holes and supergiant elliptical galaxies. New telescopes will provide sharper images and more detailed spectra. Gravitational wave observatories may one day detect waves from mergers involving black holes of similar mass, providing direct confirmation of processes that are currently inferred from circumstantial evidence. Advances in theory and simulation will allow more realistic modelling of galaxy mergers and black hole growth, testing whether our current understanding can explain the formation of objects as extreme as Holmberg 15A. Through it all, this distant galaxy, a faint smudge of light in the constellation Cetus, will remain a beacon, guiding us toward a deeper understanding of the universe and our place within it.